Hello, everyone. Welcome to the August 2024 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. I can't believe it's August already. As I'm recording this, it strikes me that the next time I record an AMA, it will be the semester already started here at Johns Hopkins. Our first day of class is actually the first Monday in August, the last Monday in August. Sorry about that. I am obviously, kind of scrambled and scared of the beginning of the semester. I don't want to say it's a love-hate relationship with the semester, but it is a love-dread relationship with the semester. When I was a research professor at Caltech, I didn't care about the semester coming on because I didn't really do that much teaching. I didn't go to faculty meetings or anything like that. But now that I'm just a regular old professor in some senses, all those things are very, very real. And I love the actual teaching, but it does require an enormous amount of attention, where there's also a whole bunch of other things requiring their attention. So this semester, I'll be teaching two courses, one in the philosophy department, one in the physics department. They're both a lot of fun, so I can't really complain. The philosophy one will be jointly taught with Janan Ismail, who is a former Mindscape guest and also my philosophy colleague at Johns Hopkins, co-founder of the Natural Philosophy Forum. And we're teaching a graduate reading course on complexity theory. It should actually be a lot of fun. So by a reading course, we mean we are compiling some of the great papers that have ever been written in the field of complexity, especially ones that have philosophical implications, which many of them do. And we're just going to sit around the table in the, ideal paradigmatic teaching situation, since it has been since Socrates. We're going to read the papers and we're going to talk about them. We're going to hopefully try to understand them better and learn something. There's a lot, I did say this, but there's a lot of philosophical interest in complexity. What is complexity? What are the roles of things like information and emergence? This is, part of why natural philosophy is so interesting and fun, is because these are important questions, but also ones that benefit from some philosophical rigor and nuance and care. One slightly oversimplified way of defining a philosopher is someone who has more patience with the questions of, what do you really mean by this, right? Like, how deep does this go? All of these things where many people, including professional physicists, have to impatiently move past them. The philosophers are all into that, so we'll see how that goes. I think it'll be a good course, and never taught it before, so I am very hopeful it'll be a good course, but I can't actually go on the basis of past experience. And then the other course is in the physics department, and I deserve to be made fun of a little bit for this because it will be based on the biggest ideas in the universe. So the biggest ideas books, book 1 and book 2 are out, obviously. I said many times in the intro and elsewhere, the whole point is that these are not textbooks, and yet I'm going to use them as textbooks. There you go. What can you do? The point stands, though. They're not textbooks that are supposed to teach you to be a physicist. They're books that are supposed to teach you physics, including the equations, etc., as you know, even though you're not going to grow up to be a physicist. So the course will be for non-physicists. It will be for the general student body to fulfill their science requirements, learning a little bit about the equations of modern physics. So we'll see how that goes also. That's an undergraduate general course, very different than a graduate course. The big challenge there, I know already, is going to be grading. Grading is always a bit of a challenge, but in this case, it's not something you can write a paper on, and it's definitely not something you can do problem sets on. So I think I'm going to have to be like a regular old professor in the sense of giving tests in class and maybe a final exam. Definitely a final exam, I should say. I generally don't do that. I generally, for my physics classes, have always graded on the basis of problem sets and then a take-home final. Actual tests in class is going to be a new experience for me. So we're never too old to have new experiences, even as people who have been professors for a long time. Anyway, that's where my brain is at now, trying to get ready for the new semester. But let's dive in now to the Ask Me Anything, of course. I sometimes forget to say this. This is sponsored by the Patreon supporters of the Mindscape podcast. You too could be a Patreon supporter by going to patreon.com/Sean M. Carroll. It's actually very, very easy and fun to be a Patreon supporter. It's less onerous to sign up and to, pay the $1 per podcast episode than you might think if you've never gone on Patreon before. It's actually completely painless. And maybe you'll discover that there are other creators on Patreon that you want to support also. That would also be great. I have my handful that I support just because I like them myself. And if you are a Patreon supporter of Mindscape, you get to ask the questions that later come into these Ask Me Anything episodes. Once per lifetime, you get to ask a priority question that I will definitely try my best to answer. And you get ad-free versions of the podcast on Patreon. So it's a win-win-win all around. Oh, there's a little bit of thunder in the background. I don't know if you can hear this. Here in Baltimore, early August, we're in the middle of a thunderstorm right now. So I hope the power doesn't go out for sure. In the meantime, I hope that the thunder and lightning in the background is not too much noise for you. And with that, let's go. Mark Allison says, I'm not sure how to pronounce Mark's last name. Sorry about that, Mark. I'd like to hear more about the nature of information, and in particular its conservation. The example often used is the book tossed into a black hole. But suppose you and I develop a breakthrough theory of apple pie over coffee, and soon thereafter, prior to full publication, I die. What is the flow of information in that situation? You're completely legit in worrying about the definition of information or the nature of information in this sense. It's one of those words that is used in perfectly sensible ways, but are not coherent ways, not consistent ways. The word information means different things in different circumstances. So, for example, if you go back to the podcast we did with Christoph Adami, where he was talking about biological information, he will tell you that there's no such thing as information other than that which is being either measured or stored by some other system. So to Christoph, the nature of information is a relationship between two different things. And that's actually pretty close to the concept of information that we informally use. So if I have information about something, and this is more or less the apple pie example, the theory of apple pie example, if I invent a theory, what is that? Well, then I have some bits in my brain representing the structure of that theory, and no one else knows it, and I die, so that information is lost. That's kind of a macroscopic thing. That's very different than the fundamental laws of physics. If there were Laplace's demon watching what was going on, and let's imagine the world is classical, so we don't need to worry about quantum indeterminacy and so forth, Laplace's demon neither gains nor loses information when you invent a new theory and then you die and without telling anybody about it. The microscopic information that goes into every single atom and force in your body is conserved over time in classical mechanics or in certain versions of quantum mechanics. But that's not the macroscopic and accessible information that you actually think of when you're thinking of, oh, I know, who did it in the murder mystery, or I have a good theory of quantum mechanics or something like that. So those are just two different notions of information. And there are many others, right? So those are just the two that are relevant to this question. So the black hole information loss paradox is not about accessible information or macroscopic information or correlations between one system and another or something that could be useful in any way. It's about the sort of Laplace's demon level microscopic information that goes into making the black hole. So we think that, some of us think that microscopic information is conserved over time. Nobody thinks that macroscopic relative information from one system to another is conserved over time. People learn things, right? There you go. Now I'm going to group three questions together. One is from Nico LB. Why do neutron stars have such a powerful magnetic field if by definition their masses are made of neutrons without electrical charge? Where does the magnetic field come from? Walter E. Miller says, neutron stars have strong magnetic fields. Neutron stars can merge to form a black hole. A black hole can be characterized by three things: its mass, its spin, and its electric charge. What happens to the original magnetic fields from the neutron stars? And finally, George Robinson says, I'm curious about black holes and magnetic fields. I don't know why. I don't know what the correlation is. What is in the air that people ask questions that are related and about very, very specific things at different times? But here's definitely an example. Anyway, George says, the no-hair theorem tells no internal fields that can come out, but do black holes affect or distort external magnetic flux fields, like from an accretion disk or just some external galactic magnetic field? So two things going on here, but the things blend into each other. One is, how can a neutron have a magnetic field? Neutron stars have magnetic fields, and indeed, what about a single neutron? You might think, well, a neutron is a neutral particle. It can't have a magnetic field. But you got to think a little bit harder than that. Inside the neutron, there are electrically charged particles, right? There are quarks, and the neutron has spin. And a very famous thing that goes back to the days of Faraday and Maxwell is that when you have charges in motion, you get a magnetic field. This was the first hint that eventually led to relativity, right? Because you take an electric charge, which is something that has an electric field around it, you start it moving, and now you see a magnetic field. So what's going on? And eventually it was figured out that what's going on is, of course, electric and magnetic fields are unified into electromagnetic fields, and what looks like an electric field from one frame of reference is a magnetic field from another frame of reference. So for the neutron, because it is a spinning thing with charged particles inside, it has what is called a magnetic dipole moment. That is to say, it's like a little magnet. It has a north pole and a south pole because it's all these moving charges inside. The net magnetic flux around the neutron is zero, just like the net electric flux around the neutron is zero. What I mean by that is if you take a surface, a sphere, and you surround the neutron, and you sum up all of the magnetic field lines intersecting that sphere, there will be an equal number going in and going out. That's because, guess what? There are no magnetic monopoles. For an electron, if you surround it by a sphere and count up all the electrical field lines hitting it, you get a net contribution. You get a negative contribution because the electron has a negative charge. This is an interesting feature of both gravity and electromagnetism because they're mediated by massless fields. They're long-range forces. You can actually, in principle, calculate their charges not by looking at them close up, but by doing this integral, this sum over field lines far away. Because, of course, there are electric monopoles, which is why you can do that for the electrical part, electrical charge. Since there are no magnetic monopoles, the net magnetic flux coming through the sphere is zero, but that doesn't mean there's zero magnetic flux. The net magnetic flux around a magnet is also zero because that's a north pole and a south pole. But there are magnetic field lines that you can see in a little picture with the iron filings, right? All of that is true of neutrons. All of that remains true when you combine the neutrons together to make a neutron star. So you absolutely can support a net magnetic field, even though it's not a monopole. It's net zero magnetic charge, but there's absolutely magnetic field because there's electrical charges in motion. Now, what happens if you take that neutron star and collapse it to a black hole? So first, let's ask the question, in principle, could a black hole have a magnetic field? So I'm going to predict that you know the answer secretly. There's a sort of cheap answer that you already know because we just said electric fields and magnetic fields are the same thing looked at in different frames of reference, right? They transform into each other by changing your reference frame. So you know that a black hole can have an electric field because it can be electrically charged. That's allowed by the no-hair theorems. So if you observe that electric field in something other than the rest frame, it's going to look like a magnetic field. At least there's going to be a part of it that will be a magnetic field in addition to the electric field. So in principle, nothing wrong with a black hole having a magnetic field. Now, what you really want to know is, can the black hole have that magnetic dipole moment like a little neutron? And the answer is sure, absolutely no problem, as long as the black hole is spinning. If the black hole is not spinning, so let's back up. What the no-hair theorems say is that as Walter correctly quotes, the black hole can be characterized by its mass, its spin, and its electric charge, which means that all the other quantities, including the magnetic dipole moment, can be calculated in terms of the mass, the spin, and the electric charge. That doesn't mean that the calculation will give you zero, but it means they're determined by those things. And of course, guess what? If you had a theory with magnetic monopoles, the no-hair theorem would have to be updated, because then a black hole could have a magnetic charge just as well. But we don't think that that's true. But, theoretical physicists love talking about this stuff. So theoretical physicists will sometimes talk about dyons, which have both a magnetic field and an electric field. And, if that's possible as an elementary particle, then it's also possible as a black hole. Again, no evidence for that in the real world, but it's conceivable in principle. So the other thing I wanted to say, and George's phrasing of the question about, is it the accretion disk or something like that, maybe look up on the internet just to check, what people are saying about this. Sometimes I do that. So I knew the answer to this question, but I was just curious about what the internet thinks. And the internet turns out to be terrible at this question. Can a black hole have a magnetic field? It's a very simple question. But there's complications because accretion disks, which are outside the black hole and have very strong magnetic fields, possibly, are often going to swamp any actual magnetic field that the black hole has. So don't trust the internet on this question is all I would say. And therefore, don't trust large language models because they're trained on the internet. They're just going to repeat back to you what they read on the internet. Okay, Rob Gddel says, in your reflection video on the episode with Joel David Hampkins. So what Rob is referring to is one of the benefits of being a Patreon supporter of Mindscape is that after each episode, I do a short 5-minute little reflection video about, what are the ideas that were sparked in my mind by the conversation, or what went into my thought process in starting in the first place. So Rob mentions in the reflection video on the episode with Joel David Hampkins, you mentioned that you still struggle with fully understanding Gödel's incompleteness theorems. I feel the same way, but I wonder if there's an issue with allowing to make statements within a system about the system itself. It feels like this self-referential aspect is the actual origin of all the headaches. So can't we just restrict ourselves to theories that aren't allowed to talk about themselves? Let me first actually answer the question. Sure, we can absolutely do that. I mean, this is part of Gödel's theorem, is that the set of axiomatic systems that are sort of subject to this incompleteness paradox, not paradox, but feature, let's call it a feature, need to be sufficiently powerful to talk about themselves. That is absolutely true. So the one that Gödel himself looked at was something, unfortunately for physicists, a famous book in mathematical logic named Principia Mathematica, but not the one from Isaac Newton, the one from Russell and Whitehead, Bertrand Russell and Alfred North Whitehead in the early, circa 1900 or so. They tried their best to axiomatize set theory and number theory and things like that. And so it didn't quite work because of what is called Russell's paradox, which was the set of all sets that don't contain themselves. I forget which way it goes, or contain themselves. But anyway, it was Russell's paradox, which sort of undermined a little bit the hope of Principia Mathematica to be a complete, rock solid, consistent theory of set theory, was the precursor to Gödel's incompleteness theorems. But yes, it had to be complete. It had to be strong enough to be able to talk about itself. That's absolutely true. So that's the answer. The other thing I wanted to say, it's not. I hope I didn't say, who knows what I say in these things sometimes, especially a reflection video where I'm even more casual than others. But I wouldn't quite say that I struggle with fully understanding Gödel's incompleteness theorems. I absolutely do struggle with something, but it's hard to put my finger on what it is I'm struggling with. But there's some thing about mathematical logic that I struggle with, and it has to do somehow with the relationship between axioms and models of the axioms. Gödel's incompleteness theorems, I mean, I can state them, but there are implications that sort of chase down through other kinds of things. I'll give you an example. Scott Aronson and I wrote this paper on the rise and fall of complexity in a closed system, and we defined what we called apparent complexity, which is the algorithmic or Kolmogorov complexity of a coarse-grained image. of a system. So you take a system, you coarse grain it somehow, then you calculate the algorithmic complexity. What is the algorithmic complexity? The length of the shortest computer program that will output that image or that string or what have you. And Scott noted he knew this perfectly well. He says, of course, you can't really compute the algorithmic complexity. And I was not familiar with that result. And I said, well, what do you mean? Is it hard or is it literally impossible? He goes, oh, no, it's literally impossible to calculate the algorithmic complexity as a general feature. Like you might be able to in some cases, but you cannot guarantee that it's calculable. And why? Well, the answer goes down to the halting problem. The halting problem from Alan Turing is the fact that there's no general algorithm in principle that will tell you whether a computer program will ever halt. Right? In some cases, you can look at it and go, oh, yes, that's an infinite loop. Or in some other cases, yes, that's going to end. But there's no general algorithm for saying that. So if you wanted to calculate the algorithmic complexity, the length of the shortest computer program that would do something, in principle, what you would do is start with the length 1 computer programs and then go to length 2 computer programs and march through every possible computer program until one of them output your string, right? The problem is you don't know whether some of those computer programs will ever halt. And therefore, you don't get very far in this way of searching through the space of all computer programs. And so my point is that I get all those words, but it's not in my bones. I don't instantly see, because the halting problem turns out to be very, very closely related to Gödel's incompleteness theorems. They're sort of in the same bag of kind of results of things you can't do for these sets of reasons. My favorite example is actually Tarski's theorem about truth. I love this example, and again, it's something I can state without yet quite intuiting it. And the statement is, so let's say that you have a statement P in some logical system, but then you're also able to say, quote, P is true, unquote. So there's P, which has a truth value. It's either true or false. And then there is the statement, quote, P is true, unquote. Certainly, if your system makes any sense, you would like P being true to imply that, quote, P is true is also true. And if the same thing for P is false. If P is false, then, quote, P is true should also be false. That's fine, and there's no objection to that, except you can never prove it. There is no theorem that you could ever prove, says Tarski in his result. There's no theorem of the form P, if and only if, quote, P is true, unquote. And that's just very frustrating, right? Like, I can get it, I can state it, but do I understand it? Yeah, do I intuit it? Is it in my bones? I'm not really sure. There is a way I'd like to think about Gödel's incompleteness theorem, which is to think about the space of all propositions. Not quite the way that I was originally taught it, but I think that this makes sense. Someone out there, some actual smart person about mathematical logic can correct me if this is a wrong way of thinking about it. But, in my own thoughts about statistical mechanics and emergence and also, many worlds and philosophy and things, I often think about the space of possibilities and structure on the space of possibilities. So think in, some language that you have specified for making statements, propositions about mathematics or logic. This is kind of what Gödel did. So think of that, and you can think of all of the well-formed statements in that system. So a well-formed statement means it's just grammatically correct. It doesn't mean it's true or false. It just means that it makes sense in some well-defined way, and there are usually rules for generating all the well-formed statements in a system. And then what you would like to say is that this system has a way of making these propositions, and it also has some axioms about what is true and what is not true. And therefore, in the space of all possible propositions, there is a function that says, is this proposition provable? Okay, so some will be provable, some will not be provable. And then there's another function that says, is this statement disprovable? In other words, can you prove that it is false, right? Some will be disprovable, some will not be disprovable. What you would like to be true is that these two sets, the set of provable statements and the set of disprovable statements, are exclusive. So there's no statement that is both provable and disprovable. That is basically the statement of consistency of your theory. Gödel being the troublemaker that he was, prove that you can't prove that the system is consistent from within itself, right? The system is incapable of proving its own consistency. So you can't prove that there aren't any propositions that are both provable and disprovable. What you can do is assume it, okay? You can say, okay, let's assume that our system has the nice property that it is consistent. So we cannot both prove and disprove any particular proposition in it. In that case, Gödel's other incompleteness theorem says these two sets, the set of provable statements and the set of disprovable statements, don't cover the space, right? There are propositions which don't fit into either the provable part or the disprovable part. That's not that hard to understand. I think I can understand that. I hope I got it right, but it seems understandable to me. It's like I say, it's the implications, like someone who's truly an expert in this stuff, unlike me, will be able to see the implications of this kind of result much more clearly and remember them much better than I would ever be able to. Roland Weber says, I recently finished reading From Eternity to Here. In chapter 14, you briefly present the idea of eternal inflation. Expanding bubbles of not yet true vacuum form pocket universes within an even falser vacuum that continues to inflate. I'm wondering what might be happening at the boundary between a bubble and the region without. Nothing much because it's vacuum on both sides, or a lot because of the vacuum energy gradient. Is there some kind of pressure from the inflaton outside against a slower expansion within? I totally failed to visualize the dynamics of this scenario. Well, I do want to say it's, again, totally okay to feel frustrated at failing to visualize the dynamics here. It's very, very hard to visualize the dynamics because, look, I can draw a simple two-dimensional picture, right? Here's space, 2 dimensions of space. I'm going to draw circles representing, oh, this area is inflating. It's dominated by some false vacuum energy, but this area is not inflating in between the circles or whatever. The problem is, the geometry is not Euclidean, right? The region inside those circles, where there's a higher false vacuum energy, is going to be expanding faster than the region outside. So very soon, this sort of picture, you can still draw it, but it becomes less and less an accurate representation of what's really going on. And it was already a two-dimensional simplification. So there you go. But in terms of what's between, if you have there's different regimes, I suppose. So for those of you who don't know what's going on here, you imagine there's some scalar field filling all of space, and scalar fields have what is called a potential energy, which means there's different forms of energy for a scalar field. There's kinetic energy if it's changing with time. There's gradient energy if it's changing with space from point to point. And there's potential energy, which is just forget about its changes. Think about the energy associated with the value of the field. The field, you imagine drawing some curve, V of phi. Phi is the scalar field. V of phi is the potential energy. And this is what is called a landscape, a potential energy landscape. Maybe it's sort of plateaus, maybe that there are peaks and valleys or whatever. But in principle, you can have this crazy set of potentials for all sorts of scalar fields. And if the scalar field has a lot of potential energy, it can drive inflation. It can make the universe expand quasi-exponentially very rapidly in that region. Somewhere else, where the scalar field is much lower in its potential, then either it will not be inflating or only inflating very, very slowly. So Roland's question is, what happens in between? If I have one region where it's inflating very fast, one region where it's inflating very slowly, what happens in between? And the answer is it depends on what the potential is doing in between. The original investigations of this stuff go back to Sidney Coleman and his friends in the 70s, and they worked in what is called the thin wall limit. So if you have a relatively big barrier between two different minima, so you have like a false vacuum and a true vacuum, two regions of V of phi where you are locally in a minimum, and then a noticeable barrier in between them, then this field wants to be in the vacuum state in some overly teleological language. So you want to be either in the false vacuum or the true vacuum, and the region in between kind of shrinks. So it literally becomes like a domain wall, like a little wall with some energy density, and it's going to have some motion. It's generally going to move in the direction of the higher energy density. So it wants to sort of the field, again, wants to be in this lower energy, so the low energy region will expand into the higher energy region. But there are also much fuzzier cases where there is no barrier between the high potential region and low potential region, and then it becomes hard and you really have to do a numerical simulation or something like that. It will generally look like a mess where there's all sorts of different values all over the place, and general relativity and the expansion of the universe matter, and so you're going to have to do a lot of work to understand what's going on. Nicholas Weiberg says, what is your advice on dealing with climate skeptics, in particular those who claim to have read trustworthy reports that debunk climate change? I'm not well informed on climate science myself, but I'm convinced about climate change by the reports in the media and by seemingly trustworthy sources such as the IPCC. Well, you should be convinced because the vast majority of trustworthy climate scientists take climate change very seriously and attribute its largest cause to human actions of various sorts. So because of that, right, I guess there's two things to say. One is what I just said. The vast majority of respectable climate scientists say that. The other thing is we live in a world of incentives, and sometimes the incentives incentivize us to not believe the truth. In particular, if you are the owner of a fossil fuel company who makes money off of spewing greenhouse gases into the atmosphere, then you are highly incentivized to make other people not believe in the consensus truth of climate change, despite all the evidence. And for what it's worth, those people are not, just in their mother's basements. They tend to have resources. They tend to have money. So they can dig up the occasional contrarian scientist and, say something negative about climate change or about the conventional wisdom on climate change. And I don't want to put everyone into those two buckets. There are absolutely principled physicists, atmospheric scientists, geologists, ecologists, whatever, who are skeptical of anthropogenic climate change. It's just there are very, very, very few of them. And when they exist, their voices are greatly, greatly amplified by moneyed interests, okay? So anyway, what do you do with your friends who feel that way? That depends on your friends. That depends on their attitude. So are they, and this is true, forget about climate change, it's true about any issue where there's sort of a vast scientific consensus on one side and some minority voices on the other side, trying to be different. Why does your friend believe this? Or people, I shouldn't say your friends, but why does someone not want to accept the overwhelming majority of scientific opinion? And the reason why I say that is because many of these people are simply not going to be talked out of it by evidence, right? The evidence is not relevant to their thoughts. They have figured out what they want to believe. There is more than enough little evidence out there for them to hold on to that and ignore everything else. And you're not going to change their mind, no matter how much you might try. So the question is are they the kind of person who is like that, who is absolutely stuck in their beliefs, or are they legitimately questioning what is going on? And look, if they are legitimately questioning what's going on, then in the sense that they're open to possibly changing their minds if they have good evidence, I don't know what better thing to do than to point them toward the good evidence. I mean, I don't have any rhetorical tricks. I don't have any noises you can play in the background that make them more receptive to listening to scientific evidence or whatever. I just don't know what to do. But there's plenty of evidence, whether it's the IPCC. We've had people on our podcast, most recently Gavin Schmidt, but previously Michael Mann and others, Ramez Nam, who have talked about this in great detail. Look at the numbers. Look at the numbers of scientists who think one thing versus another. Because look, you can always, for anything that you might want to claim about science, you can always find a plucky minority of contrarians to deny it. The fact that such people exist is almost no evidence at all. I would be weirded out if none of them existed, right? And it's the incentive structure that gives those people a bigger megaphone. Other than that, I honestly don't have any great advice. I'm sorry about that. Paul Hess says, I had the good fortune to travel to Oxford this month and stopped in on the History of Science Museum there, and it got me thinking. You stated that there's no room left in physics for things like gods or souls because within all relevant energy ranges and scales we understand all the forces, and there's no room left for something else. I imagine prior to quantum understanding, we could reasonably make similar statements based on our understanding of Newtonian mechanics and the science of the time. In both cases, a well-educated, rational-minded person of the time would have no good justification to believe in things such as gods or souls. On the other hand, when our species first roamed the plains, there were plenty of good rational reasons to use beliefs such as this to help model our world, such as anthropomorphizing weather and predators. My question is, at what point along our path of understanding the world would it no longer be rational for a well-educated person to have these types of beliefs, based on everything known of science at the time? So again, the actual answer to your question is there's no hard and fast date. Like you can't pinpoint, at this moment we realize that you can't do that anymore because evidence and science and credences don't work like that. They creep up somewhat gradually. So I can't point to any actual date. But the more important thing is the thing that I say about quantum field theory and the laws of physics underlying everyday life could not have been said by someone who was working in the Newtonian mechanics world 200 years ago. Absolutely would have been illegitimate for lots of reasons. We didn't have a theory that even purported to be a complete theory underlying everyday life, right? We didn't understand electromagnetism. We didn't understand the stability of matter and a whole bunch of other things. Once we did understand electromagnetism, we realized we didn't understand blackbody radiation and other such things. There were always things that didn't fit the model in a fairly dramatic way. So you could hold out a hope that you would eventually be able to fill in all of the details and understand the world, but it would have been completely illegitimate to say, we understand the world so well that there is no room for these supernatural forces. That was just not true. Indeed, in the 19th century, there were all sorts of other kinds of forces and influences and fields that people did imagine. The ether, phlogiston was supposed to be this fluid that was relevant to oxidation and combustion. Caloric was this fluid that was supposed to be relevant to heat. Elan vital was a force supposed to be relevant to life, right? So, and that was there's no knockdown argument to say there's no way for that stuff to interact in a way that we would have noticed it already. It really became a makeable argument, the argument I tried to make, once we understood quantum field theory. It is the argument that I make about the laws of physics underlying everyday life being understood is not just, wow, we know so much. There's just no room for anything else. That's never been the argument. The argument has to do with the specific structure of quantum field theory, making implications about experiments we haven't done yet. Quantum field theory sort of says, if you do these experiments, then, as long as quantum field theory remains true, you can make the following predictions about these experiments that you haven't done. That's a kind of thing because of things like crossing symmetry and so forth. And that's a kind of thing that just wasn't there in the pre-quantum field theory world. So maybe sometime around the 1950s, if I need to put a date on what you're talking about. But again, it still does creep up on us somewhat gradually. Natalie Lines says, do you have any thoughts on logical positivism and the general work of the Vienna Circle? I'm visiting Vienna next week. Vienna sounds great. I've never been to Vienna. I've been to Austria very, very briefly, but never to Vienna. I want to go someday, so I'm jealous that you get to go there. My thoughts on logical positivism and the Vienna Circle are not that well developed, so you should not take any of my thoughts very seriously. My vague thoughts are that they had a very admirable goal and it didn't work. And, they had more than one goal. I mean, part of their goal was following Wittgenstein. Wittgenstein in the Tractatus tries to make a claim that many issues that we think of as deep philosophical questions are just we're speaking language fuzzily. right? We're using ordinary language in a way that is misleading to us, and we need to clear up all of those imprecisions and speak more logically. And the logical positivists sort of took up this challenge and tried to do that and tried to develop a way of thinking logically, speaking logically in particular. And Wittgenstein himself never thought that it worked. He changed a lot of his ideas along the way to writing the Philosophical Investigations and other things. And the wider philosophical community never quite thought it worked either. Still there's some attraction to the idea. I mean, let's put it this way. I still 100% believe that Wittgenstein's early point about many, many philosophical problems being based on linguistic misunderstandings is very powerful and very, very true. I would not say that all such philosophical problems have this property. Wittgenstein himself might have had that opinion at one point in his life, that the whole job of philosophy was to be so good you didn't need philosophy anymore, just sort of a therapeutic overcoming of the philosophical problems. But I don't think that that's true. I think they're legitimately substantive problems that philosophers tackle. But we should still strive to speak more logically. I think that's a good thing, not a bad thing. The other thing that is often associated with positivism, and here I think that people argue about it, and since I'm not an expert, you shouldn't believe what I'm saying, but the idea that we should pay less attention to underlying mechanisms and more attention to the ultimate prediction for observable things. The positivists were kind of, they were accused anyway of being instrumentalists. In other words, I don't care what your theory says happens, I just care what it predicts. I don't care about the gear wheels turning inside the black box. I care what the predictions are that the black box spits out. And I think that that's a little bit, my impression is, I should say, that that's a little bit unfair. They were a little more nuanced than that. But that part of the whole shebang, I actually have little sympathy for. I do appreciate that there can be more than one way to make the same set of predictions, but there are different ways in which there can be more than one way to make the same set of predictions. There can be two theories that are equivalent to each other, like truly mathematically equivalent, that make the same predictions, like, Hamiltonian mechanics and Lagrangian mechanics, at least other than some very tiny set of exceptions. These theories can be proven to be mathematically the same, even though they invoke very different words. Hamiltonian mechanics is all about positions and momenta and an initial value problem. Lagrangian mechanics, for those of you who don't understand these words, you should read Space, Time, and Motion, the first book in the Biggest Ideas series. Lagrangian mechanics just talks about trajectories and looks at them not as initial value problems, but in terms of the whole trajectory all at once, talks about actions rather than energies. So it's a whole different set of words, but mathematically equivalent results. In that case, then I'm entirely happy to say it completely doesn't matter which of the underlying theories I take as true. Indeed, I would argue that you shouldn't attach too much ontological reality to concepts that are unneeded in a mathematically equivalent statement of your theory. But there are other cases where, there are two theories that are actually saying something very different about how the world works, and it's just that you are so far unable to perceive those differences. Like an objective collapse theory of quantum mechanics says something very different than many worlds does about what the world is. The fact that I do not know how to experimentally test those or perceive those differences quite yet shouldn't make me think that they're exactly equivalent to each other. So I think that's a complicated thing. And I think that this was the single biggest reason why logical positivism did not take over the world, is because the world is complicated. The world is very often more complicated than physicists and engineers and philosophers want to make it out to be. Things are messy, and especially the process of science is very, very messy. So short version, logical positivists were very admirable, trying to do good things. Don't really think that they succeeded in completely doing them. Thomas Leighton Byers says, do you feel that gridlock between advocates of different climate remedies is paralyzing our response to climate change? It seems that the advocates of raising carbon costs/taxes are thwarted by people who oppose regressive taxes. The people who want solar energy are thwarted by people who don't want government subsidies for homeowners, or by people who want to raise tariffs on inexpensive solar panels from China. And the biogeoengineering folks are opposed by people who want to force lower carbon use. You know, I think that there's something to that, but I don't think it's the biggest thing. Certainly there is. So let's give one very specific example. There are people who want to fight climate change by putting something in the atmosphere that would reflect light from the sun and cool off the earth, okay? Now, that is hard to know what that's something that is very tricky to imagine doing, because there could very well be unintended consequences, right? Messing with the atmosphere in that very dramatic way, might do what you want to do, might also do things you didn't want it to do, and I'm not quite sure how trusting we should be right now in the state of the art. Again, I'm not an expert on this, so maybe someone else knows. I just did go to a talk recently by someone who was talking about the effect of climate change in India, where India is both pretty hot and also has vast regions that are poor as well as regions that are not poor, but the damage that will be caused to India by climate change is going to be enormous, not to mention nearby regions also being hit very hard. And so this guy, like in the first half of the talk, he was some detailed talk about the economics of the impact of climate change. The second half of the talk was all about, so we need to do whatever we can as soon as we can possibly do it. And if that means seeding the atmosphere, then we better do it. And he also mentioned that you can't just seed the atmosphere over India. Like if you seed it to reflect light, it's going to spread over the whole Earth pretty quickly. So this has to be a global thing. Other people are reluctant for these reasons, and his argument is you're reluctant because you don't live in India and you're all comfy where you are, relatively speaking. So I think it's reached already the crisis point already. Now, there's another argument besides the argument that we don't know all the consequences of that. There's a more socio-political argument against that kind of advocacy, which says if we dump things into the atmosphere to reflect light, that will lower the pressure that we have to cut fossil fuel emissions, and therefore we're going to get right back into the same problem we had before. That, I don't know if I buy that argument. So it would be true, right? If we dumped things in the atmosphere, seeded the atmosphere to reflect light, and that actually worked to lower the temperature without causing any dramatic, bad, unanticipated consequences. It would be a shame if we did that and then just kept dumping fossil fuel gases, greenhouse gases into the atmosphere and undid all the good we had done. Just started an arms race between fossil fuels in the atmosphere and reflecting particles in the atmosphere or whatever. But I'm not completely convinced that that is the real worry, because I think that we have started down the road to replacing fossil fuels with less damaging ways of making energy. It's easy to undo that progress, as we've seen with people who want to do enormous amount of fossil fuel burning to power crypto mining or AI farms or whatever. Google has basically given up on their pledge to become carbon neutral because they realized, oh, no, we can't be carbon neutral. We have to do a lot of AI, and that's going to cost us, a lot of fossil fuels. So they just gave up on it. There you go. So that's real. So I think it's very complicated. This is why I'm a physicist, not an atmospheric scientist. But at the end of the day, I kind of want to hear all of the messy discussion. I want people to argue. I want people to debate all these different things, as long as they're ultimately on the same side of making things better, right? I don't want to hear from people who just want to make the world worse. They rarely say that's what they want to do, but in practice, that's what it turns out to be. But within the set of people who want to make the world better, I want vigorous debate there, and we'll see what comes out of that. Ozren Begovic says, if we have two black holes orbiting each other in elliptical orbits and their event horizons overlap like a Venn diagram, what happens to a particle that is caught by both horizons once the black holes drift apart and their horizons detach? Would that be the case where the particle escapes the smaller black hole? I feel like this would break some law of physics. Thanks. Yes, that would absolutely break some law of physics, and basically, well, okay, it depends a lot on the details. In our good old 3+1 dimensional universe, with the laws of physics as we understand them, the simple answer is black hole horizons never detach. Once two black holes touch each other, so their horizons start to overlap, you instantly have one big black hole. They just come together, they coalesce, and they can never break apart again. If they were to break apart again, that would violate the area theorem of general relativity, because the area of the event, the total event area of the event horizon, can only go up, and breaking them apart would make it go down. Now, however, that's a feature of our 3+1 dimensional world. People do imagine what happens in other situations, 4+1 dimensions. You can get things called black strings, which are unstable to splitting apart, but that's much more hypothetical. I don't completely understand it. In fact, there are arguments about what the end state of a decomposing black string would be. Maybe those arguments have been figured out. I don't actually know what it is. But the simple answer for you, Osrin, is black holes don't break apart. Once they touch, they're together forever. Rob Graber says, during COVID, my daughter Liana asked an AMA question about black holes, and you kindly answered it. Liana is now 10 years old, still thinks about science, stars, and black holes, and she has another question. Could you have a black hole small enough and a star big enough that the star would destroy the black hole? I love this question because I know what the answer is, which is no. And again, we're making assumptions about physics as we understand it, the real 3+1 dimensional universe, etc. But there's nothing about a star that has any chance of destroying a black hole. Let's put aside for the moment issues of Hawking radiation and evaporation of black holes, okay? Those are important, but those are really only important when the black hole is in the middle of empty space. You know, as long as the black hole is accreting matter from the rest of the world, then it's not going to evaporate in any realistic scenario. So we can just think about a good old classical black hole turning off quantum mechanics and Hawking radiation. In that case, the whole point of the black hole is it is a one-way street. When you have the black hole, if it comes into contact with anything else that enters its event horizon, that anything else cannot ever leave. So you can't pull apart a black hole. I'm not even sure how you would imagine doing that or destroying a black hole. If you threw a small black hole into a large star, the black hole would just gradually eat up the whole star, and it would get bigger and bigger over time as it was doing that. This is somewhat related to something that people worried about when we turned on the Large Hadron Collider. They were worried that you could make a black hole, a tiny mini black hole at the LHC, and it would fall into the Earth and eat it up from the inside. It turns out there was essentially no chance that you would make that black hole, and there was essentially no chance that even if you did, it would just fall to the center of the Earth, and if you did that, it would take a very, 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 very long time to eat up the Earth, you know. But okay, it's something that we think about, and the answer is the black hole is fine. The black hole is just going to get bigger. It's the star I would worry about. Nick Gall says, is there significant evidence that realism is generally more fruitful than instrumentalism, as you claimed in your July AMA? As someone who rejects the instrumentalist-realist dualism, I'm surprised you didn't just reject the dualism as Dan Dennett did at the end of his paper, Real Patterns. Of which you're apparently a fan and which is the foundation of Ladymann's structural realism, of which you're also a fan. Quote, is the real patterns view a sort of instrumentalism or a sort of realism? I think that the view itself is clearer than either of the labels, so I shall leave that question to anyone who still finds illumination in them. Well, you know, I think that that's Dan being clever, but I think that if you're saying that I don't believe in realism, I believe in either, quote, real patterns, unquote, or, quote, structural realism, unquote, the fact that the word real appears in both of those phrases should indicate, and does indeed indicate, that those are two different versions of realism to me. I see zero evidence for any instrumentalist sympathies within either one of those two views. Both views are trying to be, in fact, both views are completely compatible with each other. They're trying to be a little bit more subtle about the question, what is real? But they're absolutely devoted to the idea that something is real. And for your actual question, is there evidence that realism is generally more fruitful? You know, it depends on what you mean by significant evidence. It's not something I can do a controlled trial on or anything like that. But I think again and again, the way that scientific progress is made is by thinking very, very carefully about the implications of scientific theories, in up to and including the parts of the scientific theories that give you the detailed mechanism about what is happening in the real world to lead to some prediction. We talked just a bit ago about instrumentalism in the context of the logical positivists. They, at least one view of them, again, I don't want to attribute false things to the positivists, but one view of them is they just wanted to care about what is seen in the experiments, not what goes on underneath. And many scientists, I should say, are quite sympathetic to this view. Famously or infamously, Steven Weinberg, one of the best scientists of the 20th century, wrote a very influential general relativity textbook where he took a very particle physics-y approach to general relativity. So much so that he said, all this talk about geometry and differential geometry and curvature and things like that, that's not what general relativity is about. And in the intro to his book, he says, he thought of general relativity as a field theory, and you should think of it as a field theory, he says, with a Lagrangian, and you can solve the equations and make predictions. And he has this line at the beginning of the book where he says, it doesn't matter why a certain beam of light is deflected in your theory. What matters is where do you predict the dots will appear on your photographic plate. That's a very instrumentalist point of view. It's also one I think that is highly non-useful. If you want a little bit of evidence, in Steven Weinberg's very good general relativity book, he doesn't talk about black holes, even though it was written in like the early 70s, where we were already talking about black holes. I can't promise you this, but I think that taking the geometric point of view of space-time seriously leads one to take black holes seriously in a very direct way. In my own work, I think that taking the foundations of quantum mechanics seriously leads one to ask questions about the nature of quantum states and their evolution that one wouldn't otherwise ask. So, Richard Feynman famously said that two theories can be have all the same predictions but be morally different. And I think I completely agree with what he was getting at there. Like, taking theories seriously is an important step to improving on those theories. I don't have, vast reams of evidence to show you from the history of science toward that, but I deeply believe that is true. Bits plus Atoms says, I sometimes get frustrated by philosophy because it seems that every question reduces to a previously unanswered question. E.g., I know you want to understand if that action is wrong, but what does is really mean? After reading Quanta and Fields and thinking about effective field theory, I wonder about some sort of ultraviolet cutoff in philosophy, a way to get a result without an infinite definitional or contextual regress. I suppose the question is, how do you make progress on philosophical questions when it seems that sometimes there is no place to stand? Yeah, so this is one of those questions where I like the question even though I don't have any specifically convincing answer to it. It's a fun way of thinking about sort of infinite regress problems in philosophy. If you go back to my book, The Big Picture, I tried to present an explicitly anti-foundational account of knowledge. So you say at the end, sometimes there is no place to stand. Yeah, so that's true. Going back to Descartes, there's always this hope that we would be able to establish some completely reliable, rock-solid foundation for all the rest of knowledge. Descartes himself ended up believing in God to do that. That was less persuasive to certain other people, including myself. And indeed, I would advocate just not looking for that. There is no once and for all foundational place to stand. What you're looking for are sets of ideas that cohere together, that play well together, that form some consistent system where you can sort of fit different puzzle pieces together in a useful way. So I do think, that's why when we talk about things like, why is there something rather than nothing? And I say, well, probably there's no answer to that question. Not in the sense that we don't know the answer, but probably there is no thing or feature or property which plays the role of the reason why there is something rather than nothing. Okay, you can't demand that there is such a thing. Maybe there is. That's completely possible. I haven't heard any good suggestions, but it's always possible. But it's also possible that such a thing just doesn't exist. And so I think that these philosophy games of trying to define words very carefully and being very persnickety, they actually can be very valuable and play an important role, because outside of philosophy, people are often very sloppy. And that's often fine because, look, if you write a computer program, you can't write every computer program in assembly language, right? Sometimes you need a higher level interpreted language to actually make progress at any reasonable rate. Likewise, in science, you can't always go down to the very foundations of everything. Sometimes you need to take some assumptions on board and move forward, and that's fine. But there is also a place for assembly language. There is also a place for digging into the meaning of all those words, because you might realize you are misusing them a little bit, and that might help you move forward in a productive way. Marie Rouskew says, people used to ask me if I really do believe in quantum mechanics and or general relativity like it has been a belief/religious thing. They argue that I can't prove its existence and that I use Einstein and Schrödinger as prophets. Do you have similar experiences? What would be the best answer to explain that science and religion are two different things? Yeah, I think that they're very different things, and I wouldn't even phrase it as science versus religion, because religion means different things to different people. There are parts of religion that do try to be evidence-based, etc. So I'm not going to get into that. But I do think, and I think that maybe I'm in a minority here among my friends, but I have no problem with the word belief. There is a difference between belief and unjustified belief. Just because I have a belief doesn't mean the belief is unjustified. Maybe I have a belief for very good evidence-based reasons, right? A belief is just, a degree of belief is a credence in a proposition. I have no trouble saying that I have beliefs and I believe in quantum mechanics and or general relativity. That does not mean either that I believe them with no evidence, nor that I wouldn't change my mind if other evidence came along. All of that can be true at one time. So I would say don't cede the ground of saying that you do believe in general relativity and that somehow sounds wrong. That sounds fine. You believe it until something better comes along. That just means you put high credence in that proposition, and the credences will change when new evidence comes in. Also, finally, and I'm being the philosopher that was just complained about by Bits plus Atoms, but you got to define what all these words mean, okay? And the other word is proof, right? They argue that I can't prove its existence. Sure, you can't prove its existence. Science never proves anything. That's not the job of science. The job of science is to figure out what is the best explanation we have available to us. That explanation will never be 100% established, because if you assigned a credence of 1 to some proposition, then no new evidence could ever change your mind. That would be bad. That would not be a good scientist. So the idea isn't to find proof of its existence. The idea is to find evidence of its truth against other possible alternatives. So do you want evidence that quantum mechanics is true or general relativity is true? Oh my goodness, there's so much evidence. I don't even know where to put it, right? I mean, going back to the early days in quantum mechanics, predicting the spectra of atoms or the stability of matter, and general relativity, predicting the precession of Mercury or the deflection of light. I don't know what to say. There's just so much evidence. It's just so obvious. How can someone even worry about that? Of all the worries to have, that's not one of them. In fact, if you wanted to have some difference to highlight between science and religion, maybe that is it. The fact that science doesn't prove things. The fact that science is always willing to change its mind when new evidence comes up. And this shows up in the practice of the discipline, right? I mean, there's a joke, a little bit of a joke, but there's some truth in the idea that if you write a book arguing that the Pope is wrong, you get excommunicated. If you write a paper showing that Einstein is wrong, you win the Nobel Prize. That's the difference in attitude between the two fields. Peter Blankenheim says, digital technology has given us a million ways to click ourselves into opposing silos and attack each other with click darts, pushing polarization to the top of social interaction. You and your physics of democracy students must discuss ways to make technology more civil society friendly. Consider, for example, a widely distributed free organizing app which encourages people to seek consensus across political lines locally on popular but stubborn issues like a gun safety amendment, then saves their progress and contact info to a national hub to be continued and expanded on across state and generational divisions. Do you have thoughts on specific projects or general direction for this type of reform? I don't really have that much thoughts, other than I would like to see efforts in this direction. That sounds great. But until an effort shows up that actually works, I'm going to remain somewhat skeptical. I don't think that finding that correct app is necessarily the solution to our current polarized system. I think that there are systematic forces that push us toward polarization. Most obviously the political system, most obviously the winner-take-all presidential election system, where it trickles down into things like geographic polarization, right, between urban and rural divides and things like that, which we've talked about on the podcast before. But most seats in the U.S. House of Representatives are very easy to win once you're in, right? The incumbent is going to win every single time. Certainly the incumbent party is going to win every single time. And therefore, there's not a lot of incentive for political leaders to try to reach across the aisle. You want to win your party's vote, not the overall vote. And the presidential system means that there's no real space for a third party to be healthy and thriving. So I think that there's other aspects also. Technology definitely does play a role, but I don't think that there's going to be one technological thing that by itself is going to fix things. The fact that parties have become more aligned ideologically, that is to say, within any one party, there's a lot more ideological coherence than there was 50 years ago. That plays a huge role in this polarization stuff, and I'm not quite sure how to fix that by getting people to talk to each other on a new app. Chip C says, based on hearing your podcast, I think your take on morality can be summed up like this. As a moral anti-realist / constructivist, you understand moral rules as not having any kind of objective existence like tables and chairs, but as being constructed by individuals or societies based on reasons that they find persuasive. You deny that it is possible to derive aught from is. Perhaps one reason that I and many others are not convinced that this is the best way to think about morality is that the consequences for individual and societal decision-making are so radical. It seems you treat beliefs about moral norms like any other matter of taste. I may find some musicians to be better than others and have very good reasons for my preferences. However, I realize that trying to convince others or force them to adopt my musical tastes is pointless. It seems like you and some other moral constructivists that I read don't grapple directly with the most disturbing consequences of your position when taking to its logical conclusion. For me, these consequences are a barrier to adopting an exclusively materialist view of reality. Have I misunderstood your thinking? I don't think you've misunderstood my thinking, but I do think that your actual argument does not carry much weight for someone like me. What you're saying is that if morality is not objectively grounded in features of the universe, then people can pick their own moral views, and they might not be the ones that you want them to pick. To which my answer has always very consistently been, yes, they can. And in fact, they do in the real world. So you're not describing your disaster scenario isn't anything other than the world in which we actually live. But more importantly, who cares? You cannot argue against a point of view in metaphysics or ethics or whatever by saying you don't like its implications. You have to argue against it by saying that it's not true. Quantum mechanics implies that you can build an atomic bomb. That doesn't mean that because I don't want atomic bombs to be built, I should not believe quantum mechanics, right? I can't just say, if this view is true, I'm not going to like the consequences, therefore I'm not going to believe the view is true. You have to actually provide an argument as to why the view isn't true. In fact, let me add to that. I think that it's exactly the opposite. I think that the point is that people want moral objectivism to be true very, very badly for exactly reasons like this, and that leads them to not think very hard about the fact that it's not true. Furthermore, I keep coming up with more things to add on here. Once again, look at the reality. To say that there is an objective moral truth or a set of objective moral truths is not yet to tell me what they are. And it turns out that plenty of people run around claiming to have found these objective moral truths and lead to things that I personally think are terrible, right? Authoritarianism, repressive societies, intolerance based on the idea that these people have the once and for all moral truth. So as an empiricist, I think that the consequentialist argument works against people like this, but it's also not the one that should matter. David Jackman says, are there problems with the use of computer sciencey terms in theoretical physics? I sometimes see ideas that feel very familiar to me as a software architect, such as computational complexity or even bits with regard to information and entropy. On the one hand, this seems to help me feel grounded in understanding the subject matter. On the other, it concerns me that something is being hand-waved or lost in translation. Well, you're going to, I'm answering this question because I think it raises some interesting ideas, but you're going to have to be way more specific about what your actual worry or objection is. As a matter of fact, ideas like bits and complexity and entropy and information are used in physics all the time, and they're super useful, right? They help clarify the situation. Now, as we've already seen in a previous question, they can also help obscure things if you're not clear about what your definition is. But the solution to that is not to not use terminology that crosses intellectual barriers, but to use it precisely, to use it well. So I'm all in favor of being clear when you use these words, but I'm not in favor of not using them because there's the possibility that someone will misunderstand. I'm in favor of trying to decrease the probability that someone misunderstands. Nate Wadoops says, is there any scale of structure for which cosmologists expect the gravity that pulls things together to exceed the dark energy that pushes things apart forever? For example, at the galaxy scale or at the atom scale or somewhere in between. You know, I hesitate to answer questions like this because the words used, they're very natural words to use about pulling things apart, pushing things together. It's not really the way the things work, right? The real way things work is that there are equations. Einstein's equation in this particular case, and you need to solve the equation, and the geodesic equation also. We attach words like push and pull after the fact, and this is exactly what the previous question was worried about. You can sometimes, in using these words casually, get mixed up because there are implications of them. So that's just a big caveat to even answering these questions. But the spirit of the question I can actually answer because, yes, there is a scale. It's not set once and for all. It depends on, let's back up and be clear. You start in the early universe, not the super duper early universe, 10 to the minus 10 seconds after the Big Bang, but 100,000 years after the Big Bang. So you've had some time to cool off. There are density perturbations, right? So the universe is pretty darn smooth at this era, but it is a little bit more dense in some regions than in others. A little bit underdense somewhere, a little bit overdense somewhere. Those are the density perturbations. And the particles that make up matter, right, the hydrogen atoms, the dark matter particles, whatever, are on average moving apart from each other. That's because the universe is expanding. And of course, it's more complicated than that because actually there aren't hydrogen atoms yet, 100,000 years after the Big Bang. There's protons and electrons. On average, they're moving apart from each other. But in fact, the individual protons and electrons are moving faster than the overall expansion rate, so they're crossing past each other. It's a high temperature plasma. Eventually, 380,000 years after the Big Bang or something like that, you cool down enough to make atoms, and then you can make the statement that I made. So it's not that so much that dark energy is pulling the universe apart, it's that there's an initial condition that the universe is expanding quite rapidly, and that leads to this effective separation of particles. But because there is overdense regions and underdense regions, if you have a region that is overdense enough over an appropriately small length scale, then the mutual gravitational force between the particles in that overdense region can pull them together and stop the overall expansion within that region effectively. And if this happens in two regions, then those two regions continue to separate, so there's still overall expansion of the universe. But within what we call the bound region, where the gravitational force is strong enough to keep things together, there is effectively no expansion of the universe anymore. And so you can ask the question, what is this scale on which, in fact, what you should think of it as is, any two test particles, two little atoms that you have in your brain. In the early universe, they're moving apart and they're pulling each other together. And depending on the details, depending on how much matter perturbation there is, how much density perturbation there is, and depending on the expansion rate of the universe, either that pulling together will win or it won't. So either these two particles will continue to move away forever, or they will reach a maximum separation from each other and start moving toward each other and eventually form some kind of bound structure. And so, so if you have a very, very dense region, then it can be quite large, and that can happen. If you have a not very dense region, it has to be quite small for that to happen, because then the mutual separation velocity is a little bit smaller. Roughly speaking, this leads to a maximum size for gravitationally bound structures in the universe. Clearly, a galaxy is gravitationally bound, so the maximum size better be larger than that. It is even larger than clusters of galaxies. But then once you hit super clusters of galaxies and things like that, it becomes dicier. Then it depends on the details. So whether or not things larger than clusters of galaxies are gravitationally bound is a tricky detail by detail question. So roughly speaking, you can think of very large clusters of galaxies as the largest bound structures in the universe. I'm going to group two questions together. Subendu Harsh says, you've mentioned before that the fine-tuning argument is the best argument for God, and it is still bad. Still, I struggle to understand the anthropic fine-tuning argument for the existence of an intelligent designer. Isn't it more plausible that life evolves under the given conditions rather than the conditions being precisely fine-tuned for life? Could life not adapt to different parameters, such as having lungs in our feet instead of chests, existing on a nanometer scale instead of a meter scale, or being based on unobtainium instead of carbon? And then David Lindsay says, what, if anything, would you consider reasonable evidence for the existence of God? I like to think that my atheism or any other position I hold could be swayed by sufficient evidence, but I cannot think of anything that couldn't be better explained as superior technology and or more advanced understanding of the material world. So I think you see the connection. These are not the same question. I will answer them separately, but there's a connection between them. And I think that one overall factor applies to both of them, which is that people tend to underestimate God. If God existed, God would be super powerful. Like, the idea of God is that God is omnipotent and omniscient and omnibenevolent. So it's like any view of the world where your explanation for why things are a certain way depends on arguments along the lines of, well, God wouldn't want to work that hard. I don't trust those arguments in any way, okay? So thinking about fine-tuning, the real reason why fine-tuning is not very good, actually, let me answer Subendu's question first and then tell you the real reason why it's not very good. Yes, of course, if you have many different physical conditions at different parts of our universe, then life will arise where the conditions are hospitable to life arising. It's much more likely to get life arising on the surface of the Earth than the surface of the Sun or the desolate cold of interstellar space. No surprise there. But the fine-tuning argument relies on the idea, which is very plausible but not 100% established, I would say, that there are some possible alternative values of the fundamental particle physics parameters where life would be strictly impossible. And the reason why I say that we don't know that for sure is because I don't know where life is strictly impossible or not. But the reason why I say it's completely plausible is, forgetting about the exact strength of the electromagnetic force or whatever, what if neutrons were lighter than protons? Okay. Right now in the world, protons are lighter than neutrons, which means that neutrons tend to decay into protons, and you're left with protons and electrons, and they can form atoms. And those atoms, or the nuclei of those atoms, which are protons, they can fuse together to make bigger nuclei, and the neutrons are close enough in mass to protons that if they bind together with protons in the right way, those nuclei can be stable. You're led to the periodic table of the elements and the whole bit. But if the proton was a little bit heavier, then instead of neutrons decaying into protons and electrons, you would have protons decaying into neutrons and positrons. And the positrons would just annihilate with any electrons you have lying around. And so you're left with a world with nothing but neutrons and photons, right? Maybe neutrinos and things like that. But the only massive particles, sufficiently heavy particles, would be neutrons. And neutrons by themselves don't give you very interesting chemistry, right? You can make a neutron star, but it's very hard to make a DNA molecule with no electrons, with nothing but neutrons. And that change to make neutrons lighter than protons rather than heavier protons is not some super fine tuning. It's a very easy change to make. It's a lot of phase space out there in parameter space for neutrons to be lighter. And that's not to say that you couldn't form life in a neutron star or something like that, but it would be very different than life as we know it, and it's very hard to imagine what it would be like. So I think that the traditional fine-tuning argument says that. It goes further, and they are arguing about the vacuum energy and the fine structure constant and things like that. It's often done very, very badly, I have to say. The level of scientific sophistication of these fine-tuning arguments is not very high, but I want to be fair to them, and I think that the argument is not that where our lungs are or anything like that. The argument is, can you even make a molecule? Okay. And the reason why that's a terrible argument is because God would have no trouble at all making life no matter what the fine structure constant was, no matter what the mass of the neutron was, no matter what the laws of physics are. God can make life non-physically, right? God can just assign life to rocks if God wants to, because God can do anything. The irony of the fine-tuning argument is it only works if you don't believe in God. Because God isn't finely tuned. God doesn't care about the fine-tuning of the laws of nature. The fact that in the real world we have parameters of physics that allow for very complex molecules and organic structures and living beings and so forth is a fact about physics, right? It means that without God's help, the universe can still support life. That's not an argument for the existence of God. That'd be really weird. It is really weird. People do hold it up as an argument for the existence of God, but it's not a very good one. To wriggle out of it, you have to sort of demote God to someone who is not as powerful as you thought he really was, or you have to attribute to God some wishes and desires, like, oh, but God would like it better if the laws of physics allowed for these complex structures even without his intervention. How do you know that? Why are you speaking for what God would like? That's why the whole thing gets just very fuzzy and messy. To David's question, is there anything you consider reasonable evidence for the existence of God? Look, again, let's ask exactly the same question phrased in a different way. Do I think that God has the ability to convince me that he exists? Yeah, I think that God is all-powerful. God would have no trouble at all convincing me that he exists. I mean, right now I'm staring at a can of La Croix sparkling water, naturally essenced with lime. And I promise you, and I say this very, very sincerely, this is sitting very gently on the table in front of me. And if as soon as I pause, it flies up into the air and does a 360, I will start believing in God. Nope, it didn't do it. You have to trust me it didn't do it because there's no video here. But the point is, of course it didn't do it because the laws of physics are always obeyed. God would have no trouble doing things that seemingly disobey the laws of physics. Now, given if the can did fly up in the air, could I come up with an explanation purely based on physics or natural laws? Of course I can. But that is not how reasoning works, right? That's not what it means to be a good Bayesian. You don't wait for something to happen and then say, can I explain it? That's what people who believe in God do all the time. Rather, you make predictions ahead of time. You collect data and you say, what is the likelihood of this happening under my two beliefs, under my two propositions? So, of course, it's possible that the can would jump up in the air, even according to the laws of physics. But given that I had just set it up as a test of God's existence, I would actually, it seems more likely the can would fly up in the air under the God hypothesis than under just the random physics hypothesis. And of course, you would have to do many more, et cetera, but you're not proving the existence of God or the non-existence of God. You're asking what is the best account, what is the best explanation for what I observe. And I have no trouble imagining that that account would be God, if that actually were what the universe looked like. Okay, Copenhagen Interpreter says, we know from general relativity that when two black holes merge, the mass of the merged black hole is substantially smaller than the combined mass of the two black holes before the merger. We also think that or at least some do, that when a black hole evaporates due to Hawking radiation, the information lost in the black hole gets retransmitted into the universe, thus preserving the information. How does the black hole information corresponding to the loss of mass get transmitted from the merger event? Is it encoded into gravitational waves, or is it transmitted as electromagnetic waves? Do we have a theory that describes this mechanism? There's two things going on here to be super careful about it. One is the energy that is lost by the two. You're right that when you have two black holes and they merge together, the mass of the new black hole is less than the mass of the two black holes that you had combined. It has to be that way because some energy is going to be given off in the form of gravitational radiation, and to a good approximation here, energy is conserved, right? So the energy conservation mechanism is 100% understood. It's exactly what general relativity predicts. Now, you want to think of that in terms of information, and this is the second part of the explanation. You have to be careful in thinking of that because there's no rule that says information is proportional to mass or anything like that, right? The information that is in principle taken off by the gravitational waves is quite pitiful. It's a very tiny amount of information, but that's okay. It's still, the total amount of information is still conserved. The thing about black holes is that their entropy is as high as it can possibly be for a given amount of mass, right? Black holes are super duper high entropy, which means you need a super duper amount of information to exactly capture their quantum state. But a gravitational wave doesn't need to have all that energy, so it's fine. And also, even though the mass goes down, the area of the event horizon goes up, right? We talked about this before. This is the area law of general relativity. So it's not like too much energy is lost when the black holes merge. If you take the, let's be super careful here. So imagine we have black holes that are not spinning. Okay, so Schwarzschild black holes. Then the area of the event horizon is just proportional to the mass squared. Okay, so when you take mass 1 and mass 1, you combine them 2, now you have mass 2. So what was the area before? Well, it was 1 squared plus 1 squared is 2. Now it's 2 squared, which is 4. Look, the area went up in exactly accord to, I'm very glad that worked out, this high-level mathematical calculation. But of course, some of it'll be less than that because some of the energy is lost to gravitational radiation, but not so much so that the final area of the event horizon isn't more. So if you were just thinking about the implicit amount of information from the entropy of the black holes, the amount of information in the black holes themselves goes up because you went from two smaller black holes to one with an area larger than the sum of the two different black holes. I hope that all made sense. It made sense in my mind when I was saying it anyway. Sandro Stuckey says, what inspired you to start working on the foundations of quantum physics? Was there a paper or book that sparked your interest, or maybe discussion or collaboration with a philosopher? What was your first publication on the subject, and who did you write it with? Well, I was always mildly interested since I became a physicist. I remember when I was an undergraduate, I co-wrote a review paper with Bill Press and Ed Turner on the cosmological constant. So this is 1992, before we found the cosmological constant, but having been an author on that paper certainly helped my citation total, let's put it that way, once we actually found it. And one of the things in 1992 that was a hot topic in cosmological constant circles was Sidney Coleman's purported mechanism for making the cosmological constant zero based on Euclidean quantum gravity. Okay, I'm not going to go into the details of that. It seems to be the consensus these days that it didn't work. And it's good that it didn't work because it really did predict that the cosmological constant should be zero. And we have found that it's not zero, apparently. So, it could always work. You can always make it work. Even if Coleman were right and the real cosmological constant is zero, you just say that what we're observing today is some kind of temporary dark energy, and that would be fine. But it made me read a lot about, so that was my job. Part of my job for that review article was explaining Coleman's mechanism for the cosmological constant problem. And I did. And so that got me reading about quantum cosmology, which is this fun but sort of half-baked field, that we talked about with Thomas Hertog and probably have mentioned before on the podcast. And that's when I learned that there's an implicit connection. Everyone who works on quantum cosmology is an Everettian, someone who believes in many worlds, which is completely unsurprising because the thing that inspired Everett to propose many worlds was thinking about quantum cosmology, was thinking about understanding the universe as a quantum system. And his argument was, well, in Copenhagen, I need a separation between the observer and the system. And if the universe is my system, that separation can't happen. So, it doesn't really matter what the initial inspiration was other than for historical interest, but that was the initial inspiration as I understand the history of it. So, but I wasn't, I thought about many worlds a little bit. It seemed perfectly plausible to me, but I certainly didn't specialize in it in any way. And at that time, as a graduate student or as a postdoc soon thereafter, I wasn't thinking about foundations of physics. Then I did. So the long and winding road here is that I was very influenced as someone who cared about cosmology by arguments from Hugh Price, the philosopher, and Roger Penrose, the physicist, mathematical physicist, about the low entropy of our early universe. This seemed to me to be a real problem, and there's room for better physics in the purported solutions to this problem. So that's when I wrote my paper with Jenny Chen on the Arrow of Time circa 2004 when I was a young assistant professor. And it was only through writing that paper that I became aware that there was a field called Foundations of Physics. And, I went to a conference and I met David Albert. And later I met Tim Maudlin and David Wallace and other people who you've met on the podcast. And so then I felt a lot of kind of resonance with those people and how they were thinking about the deep fundamental questions of reality. And so that was a lot of fun. But the even bigger question in Foundations of Physics, even bigger than entropy in the Arrow of Time, is the foundations of quantum mechanics. And I never really thought about it very carefully. I was an Everettian, but not like a evangelical Everettian. I should say just not someone who thought about it in any detailed research level way. And actually what happens, and I'm sure I've told this before to some people on the podcast, but Chip Sebens, who was at that time a graduate student at the University of Michigan, who is now a professor at Caltech in the philosophy department. He was a philosophy grad student. And he emailed me out of the blue and said, I'm a philosopher of physics, and I thought it would be fun to come to Caltech and spend the summer hanging out with you folks there. And he had his own money to do it, and maybe we could work on something. And so I thought we could work on the Arrow of Time. I had various ideas that I still haven't written up about time reversibility and things like that. And as it turned out, Chip was talking to other people in the department, especially Ira Rothstein, who was actually a visitor to the department. He's a physics, effective field theory professor specialist at Carnegie Mellon, but he visits Caltech a lot. So he was there, and Chip and I and he and Ira were having this discussion about the foundations of quantum mechanics, and Ira was like, oh, come on, it's obviously many worlds, because many people in our field feel that way. And Chip explained that, actually there's some worries about many worlds. Most obviously the question of probability, right? The question of how to get the Born rule right. And Ira was not really very impressed by that argument. But so Chip and, in some conversations with me, tried to make his argument better. And in those conversations, we realized we could actually overcome those objections. So Chip was trying to argue why you can't derive the Born rule in many worlds, and going back and forth. And, a lot of it was driven by him, but we came up with a scheme where we could derive the Born rule in many worlds. And that led to my first publication in Quantum Foundations. And, that paper has become influential in that little tiny community that cares about the Born rule in many worlds. There was already plenty of other attempts to derive the Born rule in many worlds. The most common one that you'll read about is based on decision theory by David Deutsch and David Wallace, two previous podcast guests. And I think that there's a sense in which those work. Chip and I were very clear that we weren't saying that the other ones didn't work and we have a better one. We're just saying we had a different one. And, for better or for worse, the logic can be perfectly rigorous and valid, but it might not be persuasive to people if they don't accept the assumptions of your logical argument, right? So our argument for taking seriously our derivation of the Born rule based on self-locating uncertainty and things like that was it uses a different set of assumptions than the decision theory rules do. The decision theory argument does. And in fact, I think that the assumptions are better, to be perfectly honest. I think that the real objection that people who don't think you can derive the Born rule from many worlds, their deep down objection is they don't see probability there at all, right? They see a theory that is 100% deterministic. You know exactly what's going to happen. They think that there's no room to attach probabilities to what happens in many worlds. All the probabilities are 0 or 1. The wave function does it or it doesn't. And I think that that's wrong. And I think that the idea of self-locating uncertainty makes very clear why that is wrong, because you will find yourself somewhere on some branch and you will not know what branch you're on, and you have no choice if you want to get through the world of assigning a probability to be on one branch or another, if that's how the world works. So, of course, you can argue about the specific derivation that we used, et cetera, but I think the underlying reasoning is good. Anyway, thinking about that, while I was still thinking about particle physics, cosmology, stuff like that, quantum field theory, pushed me to think about the foundations of quantum mechanics more broadly, not just deriving the Born rule in a more physicist-y way rather than a philosophical way. And that's what led to things like many papers that I wrote. I mean, most obviously, the sort of Mad Dog Everettianism papers, reality as a vector in Hilbert space, but also the emergent space-time papers with Charles Tao and Spiros Mikolakis, and even papers, we wrote about more conventional cosmology, like decoherence and its influence on eternal inflation that I wrote with Kim Boddy and Jason Pollock. So it's an example, to go back to an earlier question, of how being a realist and taking the realist stance toward the wave function seriously can really influence the research you do, which is, whether it's productive or not, I leave that up for you to decide. Chris Murray says, I've heard that it's inaccurate to think of protons and neutrons as simply being made of 3 quarks. Going one step out, is it also better not to think of atomic nuclei as simply being made of protons and neutrons? Actually, it's much better to think of atomic nuclei as simply being made of protons and neutrons. Here's a hand-wavy way to think about that. Think of the difference between the mass of the particles we're talking about, quarks inside nucleons or nucleons inside nuclei, versus the binding energy, the energy that it would take to rip them apart. In the case of a nucleus, the mass of a proton or neutron is about 1 billion electron volts, whereas the binding energy is measured in millions of electron volts. So the binding energy is noticeably smaller than the mass. And what that means is you can separate them, right? You can pull apart the individual constituents, the protons and neutrons. Indeed, we do this in nuclear fission all the time. Whereas in a nucleon, like a proton, the individual masses of the particles are relatively small. The individual masses of the quarks are millions of electron volts. It's hard to there's some fuzziness in the definition there, but that's a good one. Whereas the binding energy is infinity. Because of quark confinement, it would take an infinite amount of energy to pull them apart. So if you try to pull them apart, you end up just making more quarks and antiquarks. And what this means in practice is inside the proton or the neutron, there's actually this very, very important contribution from a sea of virtual particles, of virtual quarks and gluons for that matter, as well as antiquarks. Whereas for the nucleon, it makes much more conceptual sense to think of it as a group of individual particles, protons, neutrons, bound together, but still recognizable in some way. It's not perfectly good. These are all nice visualizations that don't quite do justice to the reality. For example, when you see a picture of an atomic nucleus, it will often look like little billiard balls, right? Proton, neutron, etc. But in fact, it's much more common to have them all smushed together in a more or less spherical configuration. The individual quarks and individual quarks and antiquarks and gluons that we think of as coming from the protons and neutrons, they don't care that they're supposed to be in this proton or that proton. They're in the nucleus as far as they're concerned. So to that extent, it does make sense to not talk about the nucleus as made of protons and neutrons, but there's a sense in which it does, so it's okay. I'll mention one other thing, which is also relevant to this, which is that you can't even think of the proton and neutron really as made of particles. And that's because the mass, what can we say? Think of it this way. The mass of the quarks is smaller than the mass of the proton. So that makes sense in some sense. When you put things together to make something else up, then the mass of the thing you make is going to be bigger. But it's a lot smaller. It's so much smaller that in quantum field theory, we think of the Compton wavelength as 1 over the mass. In natural units where h bar equals 1, etc., mass is inversely proportional to wavelength, Compton wavelength. And so what that means is the Compton wavelength of a quark is bigger than the Compton wavelength of a proton. So you might ask, how do you fit the quark inside the proton? This is something we talk about in Quanta and Fields in the new book. And the answer is that what the Compton wavelength means is the wavelength longer than which it's okay to talk about this as a single particle. But on wavelengths shorter than that, you can't talk about this particular vibration of the quantum field as just being a single particle because you've increased the energy of confinement to above the energy that it takes to make new particles, in particular quark-antiquark pairs. So what's going on inside the proton and neutron, another sense, in other words, in which the proton and neutron are not just a collection of individual particles, is that the total contribution from virtual particles popping in and out of existence is actually more important in some ways than the contribution from the quote-unquote 3 quarks that you find inside the proton. All of this has a lesson, which is that, if you push it too hard, you just got to learn the equations and you got to learn what's actually going on rather than relying on simplifications. Matthew Wright says, quote, "Are there any questions left unanswered? I live in fear that will run out someday. You joked this month." So this is referring to me. Every month on the Patreon, I ask for questions, and I don't have a lot of time to wax eloquently when asking for questions, so I'll write something very simple. I was joking, what if we run out of questions? I don't actually think that is very likely, but Matthew asks, what will you do in place of AMA episodes when that happens, and how many lifetimes of the universe do you think we have left until we get there? I don't know how many lifetimes of the universe we have, but it's very many lifetimes of the universe before we run out of questions, especially because many of the questions are ones that are already in the AMAs from earlier months. People are not very good at searching through the archives. There's lots of search functions where you can look for the answers to previous questions before you ask yours. But even if you look at completely novel questions, if you think about the combinatorics of adding words together to make questions, the number of possible questions becomes very, very large very, very quickly. Even if you only restrict yourself to questions that make sense, it's still a very big number. But if we did run out, I don't know what I would do. Maybe I would read poems. That was popular when I read poems the other month. Maybe the AMAs will just be replaced by poetry reading. Who knows? Nikolai Ivanov says, we consider elementary particle fields in quantum field theory. Can we think also of larger structures like atoms and molecules as being the quantum fields of complex quantum systems? For example, the hydrogen atom as being a quantum field resulting from the interactions of the quantum fields of one proton and one electron, and similarly for the hydrogen molecule, water molecule, and so on. Well, yes and no. It is perfectly possible to think of quantum fields as representing what you and I think of as composite systems. For example, you can do quantum field theory where the fundamental fields are protons and neutrons. Heisenberg did this back in the day before we knew anything about quarks, right? And that's a very useful thing to do for certain circumstances. But the question is, why would you do that rather than thinking of the fundamental particles as just particles? In some sense, particle-based quantum mechanics is easier than field-based quantum mechanics because there's fewer degrees of freedom in a particle than in a field. We use field theory because it's how nature works, and it's the only way to be compatible with relativity and particle creation and annihilation. But you don't always have to use it. So the reason why you sometimes have so let's put it this way. What fields let you do is successfully talk about changing the number of particles. If you look at the Schrödinger equation for, let's say, a 3-particle quantum system, for a non-relativistic point particle quantum mechanics with just 3 particles, the Schrödinger equation will tell you it will always be 3 particles. The number of particles will never change. Whereas in nature, we know sometimes the number of particles does change when a atom decays, or even when an atom just gives off a photon, for example, right? Fields are very, very good at describing those cases of particle creation and annihilation. In fact, you can think of a field, you could construct a field if you want to, out of starting with 0 particle states, adding in 1 particle states, adding in 2 particle states, 3 particle states, etc., considering the entire infinite tower of those, and bundling them together to make a quantum field. It's not the most convenient way to do it, but you could do it. So that's why you don't do it for protons and neutrons and hydrogen atoms and water molecules and so forth, is because those things are big and heavy enough that it's very rare to see them being created, right? You don't see the annihilation or creation of water molecule, anti-water molecule pairs. And as long as you don't, quantum field theory is a bit of overkill to describe it, even though technically you could do it. Ted Williams says, I find it very interesting that the many worlds interpretation depicts a fully deterministic universe, where from the perspective of a conscious subject it seems incredibly undetermined. If I make a life-changing wager on a quantum coin flip, my entire personal experience will be completely up to an element of chance that doesn't really exist in the physical universe. Would I be right in thinking that in the context of the many worlds interpretation, Laplace's demon could fully know the objective reality of the universe and still have no frame of reference for knowing anything about my fate as a conscious subject? I wouldn't quite put it that way. Laplace's demon, if it did know everything there was to know about the quantum multiverse in many worlds, so if it knew the complete wave function and the complete Schrödinger equation, it would know everything about the wave function, okay? But there is no such thing as, quote, your fate as a conscious subject in many worlds. Many worlds says that you have your existence right now, and you will evolve into many future selves, not uniquely being one of them, okay? So Laplace's demon knows that. Laplace's demon knows exactly the set of future selves that you will evolve into. And there's no such question as, but which one is me, right? It knows that every one of those future selves are experiencing whatever they happen to experience. So it's just because we are not Laplace's demon that we talk the language of probabilities in many worlds. Pete Faulkner says, I've decided to reread Space-Time in Motion. During my rereading, I came across a concept that I had previously overlooked and now find confusing. In your derivation of E rest equals mc squared, you state, let's define the energy of an object in relativity to just be the zeroth component of the 4 momentum. While I understand how this definition aids in the derivation, I'm struggling to grasp the justification for defining energy in this matter. Could you elaborate on the reasoning behind this definition? Yeah, I think this is a very good question, and I certainly could have talked about it at greater length in the book, because I think if you're reading this kind of thing for the first time, it's very natural for you to think there is something called energy. And we kind of know what it is, and then there's something called relativity, and we derive all these other things. But what gives us the right to redefine energy just because we have some new concepts that we came up with in relativity? But in fact, that's not how physics works. We don't have this notion called energy ahead of time. In fact, it was really, really hard for physicists in the 1700s, et cetera, to decide what they meant by energy. They were mixing it up with what we would call momentum and other things. And so it's a concept that we invent. And the question is, what is the physical reality to which it makes most sense for us to attach the notion of energy? What do you want energy to be? Well, you want energy to be conserved. You want it to be related to what we already know of as like the kinetic energy and things like that, 1/2 mv squared, etc. So the point is that when you come along with relativity, as opposed to classical Newtonian physics, You have changed the rules of the game a little bit. There are new things that are conserved, etc. And what you notice is that the zeroth component of the 4 momentum in a collection of particles interacting with each other is a conserved quantity with units of energy, which furthermore, in the limit, where you say, I'm going to move non-relativistically, I'm going to imagine my particles are moving relatively slowly compared to the speed of light, that zeroth component of the 4 momentum takes the form of mc squared plus the kinetic energy. So if you have an energy-like quantity that is conserved and you're tempted to call it the energy, but you notice it has the kinetic energy term that you know and love, plus another term, mc squared, the sensible thing to do is just to start including mc squared as a new part of the energy. You know, Richard Feynman tells this story again of people claiming, oh, energy is conserved, and then, you know, he's imagining some 19th century physicists, and they keep realizing that the energy that they've defined is not conserved because it's going into another form of energy, so they say, oh, we're going to include that kind of energy also. That's actually perfectly fair, but when you have a new framework like relativity, you can come up with a principled definition of what you had meant all along, even though you didn't know it. That's what the zeroth component of the 4 momentum is. Sid Huff says, it's often claimed that Aristotle was the greatest philosopher of all time. However, at least in his natural philosophy, he was wrong about so many things. He claimed that the earth is the center of the universe, heavy things fall faster than light things, the heart is the center of human reasoning, rocks fall because they want to get to the earth, the natural state of an object is to be at rest, women are inferior to men, and on and on. Of course, he didn't have access to modern technology, nor did he apparently understand the scientific method, so basically he was guessing, making things up. Admittedly, he was prognosticating 2,350 years ago, but still, he put his guesses out there as truths. Why do you think he is still referred to as the greatest philosopher of all time, at least in many intro philosophy books? Well, first, I think that the idea of the greatest philosopher of all time is a little goofy, right? I would say the same thing about the greatest physicist of all time or the greatest biologist or whatever. People constantly want to rank as if it's, tennis or something like that, where you can actually play games against each other and win. It's not quite the same when you're talking about intellectuals. But Aristotle was certainly an enormously influential philosopher. Let's put it that way. Why was he wrong about all these things? Because it was 2,000 years ago. I mean, everyone was wrong about these things. It would be one thing if he were wrong about these things and a whole bunch of other people had been right about them, right? Of course, individual things, some people got right, some people got wrong, etc. But Aristotle sort of laid the groundwork for an enormous set of ideas in all of philosophy. Not just natural philosophy, but ethical philosophy, political philosophy, philosophy of drama and storytelling, metaphysics, logic. There's really an enormous amount of influence that he had. And I think that if you compare that to people who came later, it's almost impossible for someone today to have as much influence as Aristotle did, because the groundwork has already been laid. There's less groundwork out there ready to be laid. So it's not necessarily that Aristotle was the smartest philosopher of all time. I mean, you can make the case that William Shakespeare was the most influential author in the English language, but an author today knows a lot more about English than Shakespeare did, because there's a lot more out there to be known. But there's much less room for them to be influential because Shakespeare did a lot of the influential things. That's why we keep using phrases and ideas that we borrow from Shakespeare. Aristotle is the same way. Shauhin Alavi says, priority question. Priority question is that question you get to ask once in your life. I'll do my best to answer it. I have a question about the non-locality of quantum entanglement. What if someone applied conformal mapping to the spatial framework of quantum particles? In a transformed geometric sense, would you end up with particles that overlap or are close together so that they would no longer be considered non-local? Maybe we perceive entanglement as non-local because we aren't assuming a conformal universe. So I have no idea what a conformal universe is supposed to be. A conformal mapping, I understand, that's a change of variables. So you change either your coordinates or what the form of the metric tensor that defines space and time and so forth. None of that is going to have any influence on whether or not 2 points are space-like separated, okay? Space-like separated in relativity means you start with 1 point and the other point, the other event in space-time, is outside of its light cone. So I can do a conformal transformation on space-time, and the great fun thing about conformal transformations is that they leave light cones invariant. So it can look like you're moving something that is far away nearby, but you cannot make it look like you're taking something that is space-like separated and making it look like it's time-like separated, and can therefore influence the other thing. So whatever puzzles there are about entanglement in the regular way of speaking would still be there if you consider conformal transformations, etc. Not to mention the fact that a conformal transformation is a mathematical trick. It doesn't actually change the physical situation you're thinking about. Qubit says, from your previous explanations of effective field theories, I get the following essence. The infinities that show up while I go to smaller and smaller length scales do not appear in the final result for some observable quantity. They only show up along the way. In my mind, that is very analogous to calculating a derivative by finite differences. Going to smaller and smaller differences, I over the difference 1 over... I don't know exactly what's being said. There's a typo here, but that difference goes to infinity, but the final result still approaches some well-defined value. Does that simple comparison already capture the key essence of effective field theories, or is there more to it? There's definitely more to it. What you're describing is very much is closer, I would say, to old-fashioned renormalization theory. What you would do in old-fashioned renormalization theory is first regularize the calculation you're trying to do, which means put some kind of cutoff there, either put it on a lattice or cut off an energy or something like that. And then that's the regularization part that turns the infinite quantity into a finite one. And then you take the limit as the regulator gets smaller and smaller, the cutoff becomes larger and larger, whatever it needs to do to recover the ordinary thing. That's very, very analogous to good old-fashioned calculus. The brilliant thing about effective field theory is you don't need to do that. You do not need to take the limit. You can stick around with a finite-sized cutoff. That's what Wilson explained. You have an ultraviolet cutoff. You have an energy beyond which you don't include any contributions to your quantum amplitudes. And you find that that cutoff appears in your final answers, but in such a way that it doesn't appear in any physically measurable quantities. In other words, you don't need to take the limit to get a theory that works perfectly well only in the infrared, only at long distances and low energies. That's the brilliance of effective field theory. Navid Alam says, is there a single wave function for the universe? If there is a single wave function for the universe, does that imply that fundamentally there's a single unified field that's waving and all quantum field QFT fields are emergent from that one field? No, absolutely does not. So there's two things going on here. One is, and I forget whether I wanted to say this at this question or another question, but let's be clear on the definition of a field and how it's different from a wave function. A field, you will hear it said often, over and over again, a field is something that takes on a value at every point in space-time, right? So at every event, at every little point, at any one moment of time, every field that exists, the electromagnetic field, the gravitational field, the neutrino field, they all have values. Classically, they have values. Quantum mechanically, they have wave functions. But okay, classically at least, they have values. So the thing that the field is a function of, the information you need to give me to figure out what field value you're talking about is space-time. That's the thing that the quantum field is a function of. Wave functions are not functions of space-time in general. You might think that maybe they are. You might get that wrong because in the very simplest example you can think of, which is the quantum theory of a single particle, then it looks like the wave function is a function of space-time, right? A single particle with position x at moment t will have a wave function psi of x and t. But the whole point of entanglement is that when you have two particles, you don't have two wave functions, psi 1 of x and t and psi 2 of x and t. You have a single wave function that is a function of x1 and x2 and t. So that's the position of particle 1, the position of particle 2, and time. So the simple jargony way of saying this is that the quantum wave function is not a function of space, it's a function of configuration space for whatever system you have under consideration. When you have two particles, the configuration space is 6-dimensional, x1, x2. When you have a field, The configuration space of the field is infinite dimensional. The value of the field at every point is a dimension in the space of the configuration space for that field, and the quantum wave function for that field is a function of that. So fields are very, very specific. They are functions of space-time. Quantum wave functions are not functions of space-time. They are functions of the configuration space, or equally well, the momentum space or other changes of variables that you can do. So that's the difference between a quantum wave function and a field. So if anyone ever tells you the wave function is not a field, that's what they have in mind. Now, there's another question, which is maybe more what you're getting at. Is there just a single unified field? When you do quantum field theory in the real world, is there a single field from which all the other fields come, or are they all separate from the start? That we don't know. That is something that we are still trying to figure out. That's work in progress. And I will talk about it a little bit later in the AMA. So Ben Eckhart says, a lot of discussions about metaphysics or interpretations of quantum physics seem to boil down to various kinds of appeals to Occam's razor. But is there any kind of formal justification for preferring the Occam's razor solution over a more elaborate alternative, even if pointlessly so? Well, that depends on how formal you want your justification to be. Certainly you can't prove that the simplest explanation is always going to be the correct one. And I forget exactly how Occam phrased it, but it was something along the lines of not multiplying hypotheses needlessly. And it's the needlessly that is doing a lot of work there. I think that there are two empirical facts that are important to keep in mind when one thinks about Occam's razor. One is, if you have two explanations for the same set of phenomena, and you're not thinking about going beyond that, right? You're not thinking about even better explanations that will someday come up. You're just judging two explanations that you have to deal with right here, right now. Why not pick the easier one, the simpler one, the one with fewer hypotheses in it? I mean, that saves you work, saves you mental energy. You're not needlessly complicating your life. If you want to. I mean, the example I always use is there's a theory that says that all of the objects in the solar system obey general relativity, or if you like, Newton's laws of gravity, because that works pretty well in the solar system, except for the moon. The moon does not obey Newton's laws, but the moon does have an angel inside which pushes it around. And it just so happens that the angel is interested in pushing the moon around in exactly the way that it would if it were obeying Newton's laws. Okay, that's a theory. That theory is indistinguishable from the first theory that says it's all just Newton's laws all the way down. Why in the world would you prefer one over the other? But I think the obvious question is, why in the world would you ever contemplate the more complicated one if you have no point to doing it? The other point is that, as a matter of fact, simple explanations have a track record of working pretty well. Physicists trying to understand the world, whether it's classical mechanics or electromagnetism or relativity, etc., they all notice that the simple explanations ultimately triumph. That's not a guarantee that they will keep triumphing in the future. That's not a principled philosophical stance that they have to triumph or anything like that, but they have in fact done well. So as someone who is interested in being more likely right than wrong, I would advocate trying to come up with simple explanations for things rather than complicated ones if they're equally good at fitting the phenomena. Robert Henderson says it's come up a few times in your conversations on AI and large language models that these tools can only interpolate within the space of data on which they are trained and not extrapolate and be creative like human beings. I'm wondering if we really know whether humans are capable of extrapolating beyond the data they are trained on, i.e. all their experience. Or might it be the case that humans also only interpolate? And if you think that humans are able to extrapolate, can you say why you think this is and by what mechanism you think that they're able to do so? So a couple things. I don't want to say, I don't think I've ever said that large language models are not creative like human beings. They're creative in a certain sense, and I don't have a strong enough opinion about how human beings are being creative to say whether or not large language models are being creative in the same way. They are certainly not thinking in the same way overall. They're not reasoning, they're not modeling the world, etc. in the same way. They have training data in which they look for patterns and then they apply those patterns. That can come up with very creative looking things. Like we said in the Francois Chollet conversation most recently, if you ask a large language model to write a haiku about the arrow of time, it will do so very well, even if nowhere in its training data are any haikus about the arrow of time. Because in its training data, there are haiku, and there are also discussions of the arrow of time, and they're very good at sort of matching them together in ways that can seem very, very creative, okay? The extrapolation thing is something that Francois said, and I think it's on the right track, but he's trying to be simple. He's trying to be understandable, okay? Certainly it's not that hard to imagine trying to get large language models to extrapolate. It's just that they're really, really bad at it, right? They really don't understand what is sort of an allowed extrapolation or a disallowed extrapolation. It's kind of analogous, actually, to what I think is the biggest worry for Humeanism about the laws of physics. The Humean, anti-Humean distinction about the laws of physics. The Humean says the laws of physics just summarize what happens in the world. The anti-Humeans say, no, the laws of physics govern what happens in the world. They kind of bring the world into existence. And I'm a Humean for the 99% part, but the one little worry is, what about when you're talking about other possible worlds? If you think that the laws of physics just summarize what happens in our world, then how can you use the laws of physics to govern what you think is plausible or implausible in other possible worlds? Of course, I don't think this is an insurmountable obstacle. I think that you can take the laws of physics as summaries of what we see in our world and still ask what would happen if we imagine they were still true in other worlds. There's no real obstacle to that, but there's like a little tiny bit of a worry. I think that's the difference between human beings and large language models when it comes to extrapolation. Human beings have a much better idea of what the rules are, of what the so-called laws of physics are that separate reasonable extrapolations from unreasonable ones. There's no reason, and I'm going to keep saying this. I say it a lot. We'll see if anyone listens. And it's not about you, Robert, but I'm not saying that AI can't do these things. I'm saying that large language models are a very particular approach to AI that have limitations, and the limitations stem from the fact that they don't think like human beings in some ways. I'm all in favor, and so is Francois, of other more general approaches to AI, becoming creative, becoming good extrapolators, understanding the laws of physics, all of those things. It's just not the LLM approach. S. Sanders asks a priority question. Could you please describe the Aharonov-Bohm effect and what you believe its implications are for how we should think about the foundations of quantum mechanics in general and the many worlds interpretation in particular? For example, what does it suggest about what is fundamental? How does QFT accommodate it? Does it contradict the many worlds interpretation, etc.? Thank you. So the short answer is the Aharonov-Bohm effect has nothing whatsoever to do with the many worlds interpretation of quantum mechanics. It is, well, I want to say it is agnostic about interpretations. However, it really does rely on quantum field theory. And as a matter of fact, quantum field theory plays much more nicely, fits in much more easily into many worlds than into any alternatives to many worlds that have so far been constructed. So to that extent, it's evidence for many worlds, but I think that's pretty weak evidence. For those of you who don't know, here's the Aharonov-Bohm effect. If you take a solenoid, so that's a wire that is sort of coiled up into a spiral, and you push current through the wire. This creates a magnetic field inside of the solenoid and pretty much no magnetic field outside. There's always little leakage, etc. But okay, let's imagine there's no magnetic field outside. What that means is outside this spiraling solenoid, you can take a little magnetometer that would measure your magnetic field, and everywhere outside you could measure the magnetic field, say 0. No magnetic field there. But then you can do kind of an interference experiment with an electron. Take an electron's wave function, pass it near the solenoid, and you're going to detect it on the other side, so that there is a contribution from the parts of the wave function where the electron goes on one side of the solenoid and parts where it goes on the other side of the solenoid. And what you see is that the phase of the electron's wave function, which can be detected in various ways through interference, etc., will be affected by the existence of the magnetic field in the solenoid. And you can even, if you're a clever experimenter, you can arrange it so the electron's wave function never enters the interior of the solenoid. So this is where it's supposed to be difficult to understand. It's supposed to be surprising, right? This is why it's worthy of being called an effect, because the electron's wave function never goes inside the solenoid. It always stays outside where the magnetic field is zero, but its ultimate behavior is affected by the existence of that magnetic field. Oh my goodness, what is going on? So it's actually not that complicated to understand. You have to sort of let go of the idea that you never should have had in the first place, that the magnetic field is really what matters. So again, if you read the book that I recently wrote, you will learn about the fact that in modern physics, we think of the electric and magnetic fields as being based on a pre-existing field, a more fundamental field called the connection or the gauge field. The gauge field or the gauge potential, the vector potential, many, many different names attached to the field from which you can derive the electric field and the magnetic field, okay? And what you and I call the electric and magnetic fields turn out geometrically to be an expression of the curvature in the underlying gauge field, okay? So in that language, that way of thinking about it, there's plenty of reason to think that the gauge field is the more fundamental thing. When you actually derive the equations of motion, like Maxwell's equations or their quantum field theory equivalent, you need to start with the gauge field. You can't start directly with the electric field and the magnetic field. And there's other arguments along the same lines. But there's a feeling that at the end of the day, when you make observations, you can only measure things that are gauge invariant. Things that do not change when you do a symmetry transformation on the underlying gauge field. The gauge field itself, the value of the gauge field, is not gauge invariant. I can take the gauge field, I can do a transformation to it, its value changes. But nicely, the electric field and the magnetic field do not change. So, in fact, the electric and magnetic field are uniquely the aspects of the gauge field that are gauge invariant at a single point in spacetime, okay? The things that you could imagine defining and measuring at a single point that are completely gauge invariant, that do not change when you do the symmetry transformation, are equivalent to the electric and magnetic field. Okay, but you notice that the Aharonov-Bohm effect from Yakir Aharonov and David Bohm, same David Bohm who invented Bohmian mechanics for you quantum foundationalists out there, the idea is that the electron does not sit at one point in space-time. It goes around a certain trajectory. In fact, what matters, you do the experimental setup with the electron going partly one side, partly the other side, but you could just as easily take an electron and carry it in a loop. It's in a closed loop that surrounds the solenoid, okay? That's what really matters. The topology is not trivial. And in that case, you are sensitive to things other than the set of things that can be defined at a point, right? Because you've gone around a loop, and the important feature of the loop is that it is topologically non-trivial. You cannot deform that loop to a point without moving it through the solenoid. So when you started by saying the only physically important things are gauge invariant things, and then you said the only thing that is gauge invariant I can define at a point is the electric and magnetic field, okay, but what about things that are defined not at a point? What about things that are defined around a loop, for example? And the Aharonov-Bohm effect points to exactly a physical manifestation of things that are gauge invariant, but things that cannot be defined at a single point in spacetime. And once you just let that little bit of extra freedom loose in your mind, the Aharonov-Bohm effect is completely unsurprising to you. Bob Ritchie says, in our search for extraterrestrial life, do you think we should be concerned about sending out signals that could pinpoint our whereabouts and expose us to attack as depicted in the three-body problem? Well, I'll put it this way. I think we should absolutely worry that we could be attacked and easily destroyed by alien civilizations if they exist. All of history teaches us that that is something that we should worry about. And if you want to say, yes, but by definition, the aliens who are much more advanced must be nicer, I don't believe you. I don't think that is true by definition or by any argument. And the risk is large, right? But on the other hand, that cat is out of the bag. I don't think that it's really going to matter that we are sending out signals or not. We've sent out signals already. I think space is big, and I think that we don't know the answer to the Fermi paradox, but the simplest answer is that there aren't all that many powerful, technologically advanced alien civilizations out there, or if they are so dramatically different from us that they're almost inconceivable to our brains. So I don't think as a practical matter, there's a reason to go around shutting down any signals that are being sent out there to the skies. James Swift says, the solo episodes you occasionally do are always excellent. Would you ever consider polling Patreon supporters on a topic for a solo episode? Perhaps not even a very specific topic, but even a general area. Still loving the podcast. Thanks so much. Look, I'm perfectly happy to take requests or suggestions for solo episodes. The solo episodes work because I'm interested in the topic, not because the world is interested in the topic, right? I mean, that's just one of the great things about the podcast is it's not a podcast for everybody. We get a very good audience. I love the audience. It's much more sizable than I ever would have dreamed, but it's never going to be a bestseller, and I want it that way. Not that I would mind it being a bestseller, but I'm not going to try to work to make it a bestseller. I'm going to try to make it useful to the people who like it. And that usefulness is very much based on the fact that I like it and I think it's all interesting. Very probable that other people would suggest topics for solo podcasts that I would also like, but ultimately it's going to be my decision. You don't want to hear me do a solo podcast on a topic that I'm not that interested in. But any Patreon supporter, if you want to go in the AMAs or you just want to go in a private message and say, hey, here's an idea for a solo episode, feel free to do that. You never know when I will do it or not. I don't want there to be too many solo episodes because I think a lot of the added value comes from the guests, but I'm always happy to do them. It's less work for me. I don't have to find a person and interview them and all that. I can just talk. Bo Pariso says, I recently heard life described as an emergent property of Earth alongside consciousness being described as an emergent property of the brain. An analogy was given that if sandcastles spontaneously arose on a sand beach, they would still be made of the sand beach despite their emergent complexity. These comparisons make sense to me, but what do you think about them? Your insight would help me know whether I'm on the right track. Well, I 100% think that life and consciousness are emergent properties. I talk about this belief at great length in The Big Picture, if you want to read more about those possibilities. Because the point of The Big Picture was to be an argument that even though we don't know the fundamental nature of reality once and for all, there's very, very, very good reason to imagine that once we do know it, it will be within the realm of naturalism. And in particular in the realm of physicalism, if you want to put it that way, that it's just physical stuff arranging itself in different forms. If that's true, then both life and consciousness are emergent because essentially everything other than the fundamental quantum fields of the universe is emergent. So no surprise there. I must say I'm not sure about this analogy of the sandcastle spontaneously arising. It is true that a complicated sandcastle is still made of grains of sand, and that's the basic point. But the process of spontaneously arising sounds a little mystical to me, and that's the whole thing that these naturalist, physicalist points of view want to avoid. So I'm not sure if that's the best analogy for it. Dennis says, in your last episode with Daron Acemoglu, I was surprised by his affirmation that a factory with no employee should be avoided, and that technology should improve the productivity of workers instead of getting rid of them. Taking a step back, having machines produce the things we need should be good news overall for humanity, freeing up our time to do more interesting things. The fact that it has a bad impact on the standard of living of most people shows us that we have a bad organization of society, not that this use of technology is inherently bad. Do you think this is a utopist view, and we have to take the current organization for granted, considering only changes that are not too radical? Yeah, I think that it's a little bit complicated. I think that Daron is saying that the reason why that joke about the factory is bad is because, implicit in that joke is that nobody has a job, that nobody has any income, right? That the factories are making things and then they're made, but no one can afford to buy them because no one has a job. Now, if you're imagining alternative scenario, which we have done, go back, it's a ways back, but John Danaher did a conversation on the coming automated utopia, where it would be exactly along the lines of, okay, off not off source, but put the responsibility for making things onto technological things rather than human beings, and somehow spread the wealth. That somehow spread the wealth is doing an enormous amount of work, enormous amount of heavy lifting in this conversation. I'm in favor of it. I think that would be great. Some people both want and are helped by having work, by having gainful employment, whether or not it is necessary. I think that we human beings have sort of never really tried a social organization where work was optional and everyone had a good standard of living whether or not they worked. And therefore, as someone who gives a certain amount of respect to unanticipated consequences in complex systems, I can't promise you that it would be simple or easy or pain-free, right? But I'm in favor of trying it, absolutely. So, and I don't know, I suspect that Iran is just is thinking more closely to reality right now. And rather than being utopian, he's saying, look, the way things are right now, given the system, we need people to have jobs so they can make money, so they can buy goods. Otherwise, it's actually not a good organization. Casey says, I've read both of your Biggest Ideas books twice now, so I'm a little ashamed to ask this, but I somehow misunderstanding it from a big picture while reading them. According to general relativity, gravity is the bending of space-time. How can it also be a force that is quantized into gravitons if it's just a consequence of how space-time is structured? It's not like the other known forces are actually pulling things together. Things are just following their geodesics. Where did I go wrong? Well, I don't know whether I'm going to be convincing or not, but they're just two different ways of talking about the same thing. It's not that it is one or the other. As I said before with the case of Hamiltonian mechanics and Lagrangian mechanics, there can be different ways of talking about the same phenomenon that use very, very different words, but ultimately end up at basically the same place. The picture of gravity as the curvature of space-time as encoded in the metric tensor is the classical way of talking about it. If you want to imagine that you've quantized gravity, then gravitons are the individual small particle-like excitations of that quantized metric. It's always difficult. It is possible, and you can do it, but it moves against understanding things better in the direction of making things harder than they need to take a static force field and think of it as a collection of particles, okay? That is just as true for electromagnetism as it is for gravity. Can I take the electric field around an electron and think of it as a collection of photons? The answer is you can, but it doesn't illuminate anything, and it makes things much harder to understand in many different ways. So don't think of the force of gravity as due to gravitons. I mean, it is sorry, I should back up. Don't think of the macroscopic, everyday gravitational force that you're familiar with as being due to gravitons. You're allowed to think of it that way, okay? If you were thinking of two particles scattering off of each other by exchanging a single graviton, that would make perfect sense. That's something that we understand very well. But a static Coulomb inverse square law gravitational field, it's just easier to think of it as a classical gravitational field, and you're allowed to think about it that way. Again, you're allowed to think of the other way too, but sometimes one way is easier than the other. Tarun says, thank you for writing Quanta and Fields. It has been a challenging but incredibly rewarding experience reading it. In the discussion of symmetry groups, you describe the U1 group as the set of rotations in the complex plane, and the SUN groups also as rotations in n complex dimensions. What is the difference? Or if there is none, why do we not then refer to U1 as SU1? Well, since you already read the book, I can be a tiny little bit mathematical here. The point is that the U1 transformations of anything take that thing, whether it's a scalar or a vector or a matrix or whatever, and multiply it by an overall factor of e to the I theta. That is to say, a single complex number of the form e to the I theta, what we call a phase, as opposed to a magnitude. If it were r times e to the I theta with some random number, with some real number r, then it would be any random, arbitrary complex number, but a phase is one that specifically is e to the I theta, okay? So a U1 transformation multiplies u by e to the I theta. And you can define not SUN transformations, rotations in n complex dimensions, but UN UN transformations, and those are really all the rotations in n complex dimensions. But the UN transformations inevitably sort of factorize into an overall phase, e to the I theta, plus a rotation that keeps the overall phase fixed. And it turns out that, those are just two, it's easier to think of those as two separate symmetry groups, okay? I'm hesitating here a little bit because there's differences between Lie algebras and Lie groups, but that's a higher level thing. The physicists actually care about Lie algebras at least as much as Lie groups. The Lie algebras tell you the infinitesimal symmetry group transformation as opposed to the global topologically non-trivial symmetry group transformations. But anyway, your point is, the answer to your question is you can combine U1 and SUN to get UN, but you don't have to, and they can be different, so people usually treat them differently. The reason why, and what the S means is special. Special unitary means precisely that there is no e to the I theta factor. Okay, so the overall transformation that you're doing has no phase that you can pull out of it. And what that means is if you tried to invent SU1, well, U1 is just the phase. U1 is just e to the I theta. SU1 is e to the I theta without the e to the I theta, which means it's nothing at all. So there isn't really any SU1 in the same way that there's SU2, SU3, etc. Randy M. Roberts says, why did the Higgs field potential change from parabolic shaped to bottom of a wine bottle shape as the universe cooled off? How can it depend on the temperature of the universe? Yeah, that's a very good question, a subtle question that was figured out, or at least mostly figured out back in the 1970s, I think, under the rubric of the phrase the temperature-dependent potential. So for those of you who don't know or haven't read Volume 2 of The Biggest Ideas, the Higgs field is a scalar field, and it has a potential energy, as we talked about before, so it has a potential energy landscape. And the Higgs field is a doublet of fields. There's actually two fields, and they're both complex valued, so in some sense there's four fields, but okay, let's just think of them as two, make our lives easier. So two fields, and they're symmetric, which means that there is an SU2 symmetry that rotates them into each other. So if you imagine a potential energy landscape for the Higgs field, it's actually a function not just of one field phi, but of two fields, phi1 and phi2, the two components of the Higgs field. And the fact that it's symmetric under SU2 means that the potential energy, which is a function of these two variables, so it's a function like a three-dimensional height function of a two-dimensional set of variables, it has to be symmetric under rotations around the axis. And there's basically two choices for that. There are many choices, but the two that are relevant are one with the minimum of the potential being a single point at phi1 equals phi2 equals 0. That's the parabolic shape that Randy refers to. The other is if there's actually a bump near phi equals 0, then the potential can have the shape of the bottom of a wine bottle, or sometimes called a Mexican hat potential, where the minimum is actually the brim of the hat, or the bottom of the wine bottle, which is a little circle around phi equals 0, so not phi equals 0 itself. And spontaneous symmetry breaking happens when the field settles down into some particular value of the minimum. If the minimum were just at 0, that would be invariant under the symmetry. 0 does not move when you rotate the fields around, but a point on the brim of the hat does move around, so that breaks the symmetry spontaneously. Now, the usual story we tell is that in the early universe, the potential looked like the parabola, and the field was at the bottom. And then in the later universe, as it cooled down, it changed shape so that it was the Mexican hat potential, and the field moves to the brim of the hat. That motion happens at the moment of time that we call the electroweak phase transition, going from Higgs equals 0 to Higgs living at the brim of the hat. And Randy is asking, how can the potential energy change? The potential energy is the answer to the question, how much energy is there just as a function of the value of the field, right? It's just a number. Shouldn't be dependent on what time it is in the history of the universe. Well, it depends on the temperature, of course, because you could try to be fancier about it, but basically what we do is we imagine that the background in which the field lives is now this not empty space, but this thermal plasma. In other words, there's matter everywhere in the universe. We're thinking very, very early times, tiny fractions of a second. So there's a lot of matter, a lot of particles, a lot of charged particles, a lot of particles that interact with the Higgs boson as well as other things. And there's just really a lot of them, okay? More than just a little bit of a lot. And what that means is if you imagine that the Higgs field, as it does, would give mass to the other particles as a function of its distance from zero, that's exactly what happens. The masses of electrons and quarks and so forth in the Standard Model are proportional to the Higgs expectation value, its distance from zero in the potential. What that means is when you're surrounded by a lot of particles, it costs energy for the field to increase its value. Because it's basically when the field increases its value, it gives energy to all the particles around it. If there were enough particles around it that get mass from that field, then the lowest energy state would be the field being zero, because that would give zero mass to all the particles around it, and that would just cost less energy than giving a lot of mass to all the particles around it. Now, at the technical level, we approximate this story, or we implement this story, I should say, by just talking about the effective potential as a function of the temperature. Temperature giving rise to a whole bunch of particles popping out of existence, and those particles affect the amount of energy that the Higgs field has just as a function of its value. So for high temperature, that means a high density, that means a lot of particles around, that means the Higgs field wants to be at zero. That is the effective change in the potential due to high temperature. Jennifer Rittenhouse-West says, a question on the statement that quantum field theory is just a subset of quantum mechanics. A diagram in an old physics text attempted to show the validity regimes for classical mechanics, quantum field theory, and relativistic mechanics. It was a square divided into 4 equal squares. The top left square is slow and big, classical mechanics. Directly below that is slow and small, quantum mechanics. To the right of quantum mechanics is fast and small, quantum field theory. To the right of CM, classical mechanics, is fast and big, relativistic mechanics. Is the diagram wrong? Asked another way, is there anything at all non-relativistic about quantum mechanics? So yeah, that diagram is wrong. That diagram, I give props to trying to get a certain point across, but it does so in an especially wrong-headed way. And the simple way to see that it's wrong is to acknowledge that there is not a separate realm of validity for classical mechanics and quantum mechanics, or for non-relativistic mechanics and relativistic mechanics. Classical mechanics is a subset of quantum mechanics. The regime of physical things happening where classical mechanics is relevant is a subset of the set of regimes happening, of the regime of the set of things happening where quantum mechanics is relevant. You could use quantum mechanics to describe the flight of a baseball or the orbit of a planet around the sun. It's just harder than using classical mechanics. And exactly the same thing is true for relativity, right? Newtonian mechanics is a subset of relativistic mechanics. The world has no regime in which non-relativistic mechanics is correct and relativistic mechanics is incorrect. Said yet another way, if you think about just Newtonian mechanics and relativistic mechanics, by the way, relativistic mechanics is still classical, okay? So there's Newtonian mechanics, which means like what Newton said, and relativistic mechanics, which is what Einstein said. There is a regime in which they overlap. When all the objects are moving slowly compared to the speed of light with respect to each other, then either theory works fine. There's another regime where they don't overlap, when things are moving fast compared to the speed of light or near the speed of light. And in that regime, Newtonian mechanics is wrong and relativistic mechanics is right. So the regime, as far as we know, where relativistic mechanics is right is everywhere The regime, so far as we know, where quantum mechanics is right is everywhere, but there's a subset in which you're allowed to use Newtonian mechanics or classical mechanics as a useful approximation. And so we do so. And this reads, people often speak sloppily about these things. They'll say quantum mechanics is what describes the realm of the very small. But what is actually true is that quantum mechanics is necessary to describe the realm of the very small, but it can be used anywhere. There's a classical limit of quantum mechanics that describes our macroscopic world perfectly well. Mark Kumeri says, when discussing the many worlds interpretation, you've stated that we should think of space and time as existing in the worlds as opposed to the worlds existing in space and time. How do you think about the block universe under this interpretation? Should we think of one block universe that goes across all the worlds, a block universe for each one of the worlds, or both, a block universe at the individual level and at the multiverse level? I suppose the same question can be asked as it relates to the inflationary multiverse. So no, it can't really be asked as it regards to the inflationary multiverse. That's a very different thing. The inflationary multiverse is one space-time, so the block universe picture is perfectly sensible. The block universe, as it is usually stated, just doesn't make sense in many worlds quantum mechanics. Arguably doesn't make sense in other versions of quantum mechanics either, but let's stick to many worlds now because that's what we're talking about. The thing that exists in many worlds is not a four-dimensional space-time with stuff inside. It is a wave function. That wave function can, under the right circumstances, be divided up into branches that individually look like classical spacetimes. So the right replacement for the block universe in many worlds is the branching tree, right? Where you have a space-time that sort of branches into many spacetimes as time goes on. It's not that difficult to wrap your brain around, but it's definitely different. And usually when we're talking about the block universe, we just don't care too much about quantum mechanics. That's why we don't talk about it. Luc Gendreau says, we often hear in conversations about field theory that at one point in the early universe, all the fields split from one another. I've never been entirely sure what that means in a physical sense. I don't know what my question is exactly, but perhaps you can take the reins and expound on that. Yeah, I'm pretty sure I know the context in which you've heard things like that, and that context is precisely spontaneous symmetry breaking, as we talked about before. Think about, once again, the Higgs field. If you can visualize this, I'm not very good at describing the picture that you're supposed to be visualizing here. That's why you're supposed to buy the book. But again, a plane with two coordinates, phi1 and phi2, representing the two different components of the Higgs field. And the vertical axis perpendicular to the plane is the potential energy for the Higgs field, right? And the potential energy has this Mexican hat wine bottle form. And the Higgs field before spontaneous symmetry breaking is at phi equals 0. And under those circumstances, it doesn't matter what you call phi1 and what you call phi2, right? It's completely symmetric. That's the whole point of the symmetry. But after symmetry breaking, the field has moved to the brim of the hat, and it is at one point in the brim of the hat. One of the things you have to sit down and prove in quantum field theory is that the field does not get smeared all over the brim of the hat. It actually sits at one particular value. Basically because space is infinitely big and would require an infinite amount of energy for the field to spread out everywhere uniformly. So the field sits at one particular point in the brim of the hat, and now you can distinguish between two different ways the field can vibrate, right? A vibration is a little motion away from that point, and there's a set of vibrations that are sort of radial, okay? They're either toward or away from the origin of the Mexican hat potential, and that is rocking back and forth in the brim of the hat. The other direction is angular, so it is moving along the brim of the hat rather than perpendicular to it, and those two motions are now very different. Because one motion changes the potential energy, the one that is radial, the one that is perpendicular to the brim. The other one, the one that is parallel to the brim, along the brim, keeps the potential energy constant. And that corresponds to a massless particle, if you keep the energy constant, and a massive particle, if it costs potential energy to rock back and forth. Now, gauge invariance and the Higgs mechanism, et cetera, mix up what is going on there. And in fact, the massless part of the what would be the Higgs boson gets eaten up by the W and Z bosons. But the basic point is that that phenomenon of spontaneous symmetry breaking has led to a differentiation in the behavior of these different parts of the Higgs field that wasn't there before. So the Higgs field was just two different kinds of field that were exactly identical. Now it's two different kinds of fields that are different, so we say they've split. And the same thing happens with the gauge symmetries themselves. So in a grand unified theory, for example, you have a whole bunch of fields that are all invariant under a symmetry like SU5. So 5 complex components, which then break in the grand unification scheme down to SU3 cross SU2 cross U1, which is what we see today. And so before the breaking, all of the gauge bosons of that theory were exactly the same. After the breaking, the gauge bosons are very different. Some of them are SU3 gauge bosons, some of them are SU2, some are U1, etc. So that's what it means by the splitting. It's the differentiation between different fields caused by spontaneous symmetry breaking. Callan says, where do you stand on the issue of Humeanism versus anti-Humeanism? Philosophers like Tim Maudlin and Eddie Chen advocate for the idea that the laws of physics are primitive and that they explain how the universe is. Other folks like David Albert and Barry Lower suggest that the laws are just emergent descriptions of what happens in the universe and they don't predate it. I'm confused on this issue. On the one hand, I get David and Barry's point. Where do the laws exist if they aren't just descriptions? In some Platonic realm, are there meta-laws that explain the laws? On the other hand, Maudlin, etc. argue the point that these laws are producing every moment in the universe. I see the appeal of this too. So are the laws primitive, or is the universe just a brute backed with laws as emergent descriptions? So you might not have been hanging around, but I've on many occasions said that I am Humean about this issue. I'm on David, Albert, and Barry Lower's side here, both former Mindscape guests, not on Tim Maudlin's side, also former Mindscape guest. The laws, I don't think that laws have any existence in their own right. And it is, at least, if nothing else, that is compatible with my belief as an anti-Platonist about mathematics also, for very similar reasons and very similar to the very good point that you raised, that David Barry raised, which is, what is the causal effect of these laws, right? If I have an electron, I know what it does. I mean, I can poke the electron and it moves and it radiates in certain ways. So electrons exist in that very real sense. But if I try to distinguish between these two scenarios, one of which is there's just the universe doing its thing over and over again, and we describe the universe in the sense of laws of physics, versus a universe where now the laws really exist and they bring the universe into existence, okay? Well, what role did those laws have compared to the other one, right? Compared to the picture where the universe just exists. I'm not completely sure that this is an important question. I know Barry teases me because I told him long ago that I didn't care about this question, and now I kind of think that, okay, maybe I should care a little bit about this question, but I'm still not all the way there because it seems a little harmless for people like Tim and Eddie to believe that the laws of physics have some separate existence. I don't see what, if they want to believe it and it makes them feel good about the universe, then, go ahead. I don't see what good it does, but maybe it does because, as we were talking about before, one sort of metaphysical stance towards the actual workings of the universe can certainly affect how one tries to make progress going forward. So I don't see what the difference is right now, but if I were to pick, I'd be a Humean about it, and we will see which point of view turns out to be more productive. Pradeep Mangalagiri says, in the Interstellar movie, the wormhole was placed somewhere near Saturn. How can a wormhole stay stationary in reference to a moving planet? Since the whole planetary system is moving around the galactic center, shouldn't we have gone past it? So there's a couple things here to clear up. The statement, the whole planetary system is moving around the galactic center, is, half true, half not true, right? It's true in the sense that if you wait a few, whatever it is, million years, our planet is orbiting the galactic center. That is completely true. But at any one point in time, of course, there is something called relativity. You can't talk about the rate of motion of the Earth and the solar system all by themselves. You have to say relative to what, or in what reference frame are you measuring it. More importantly, though, for the wormhole question, Look, there's things we don't know about wormholes, so I will give you the conventional wisdom about it, but don't take it too seriously because wormholes probably don't exist. And if they do, macroscopic wormholes anyway, then if they do, we probably have a bunch to learn about them. But the conventional wisdom is that a wormhole is a connection between two regions of big macroscopic space that are connected by a relatively short tube, right, in space-time, which when you draw it, it sort of gives you the wrong idea, right? Because you sort of either draw a tube connecting 2 points on a kind of a plane, and the tube is necessarily going to be longer than any distance between the 2 points on the plane because planes are flat, and the shortest distance between 2 points is a straight line, not a tube that stretches out of the plane. That's why sometimes, like in the movie Interstellar, they bend the piece of paper, poke the pencil through the piece of paper, and say it's kind of like that. But then who bent the piece of paper, right? And this is all just because our abilities to visualize four-dimensional non-Euclidean geometries are not up to snuff. You shouldn't take these too seriously. So you're tempted to think of that wormhole connecting two different points as like having, made of fabric or something, being like a rubber band pulling or being pushed around or something like that. In fact, as we said before in a different context, you have to solve the equations. You have to solve Einstein's equation for this kind of thing. And my impression is, the belief is, that the mouth of the wormhole is kind of like a black hole, or even for that matter, a star or any other massive object. It has a gravitational field, and it has a location, and it's going to move around in some way. And you can sort of treat the motion of either mouth of the wormhole, either end of the wormhole, separately as moving through space-time like any other gravitating object. The danger is that it might have a negative gravitational field. That would be weird. This is one of the reasons why wormholes are a little bad, a little dangerous, but I'm not actually sure that's true. I think you can get around that worry. But basically, the answer is the end of the wormhole that you see in the movie Interstellar should be treated like any other object in the solar system. It can be orbiting Saturn, or maybe it's at the Lagrange point of Saturn's orbit or something like that. Or maybe it's in just another orbit that is similar to Saturn's but not quite the same. Any of those are perfectly legit. Johannes Pirsch says, I recently attended the Amplitudes Conference and was wondering how familiar you are with the on-shell approach and what you think of this viewpoint that makes particles fundamental again. It certainly moves away from the concept of quantum fields as fundamental and views QFT and gauge theories as more of a tool along the way to construct interacting theories with the correct local and causal interactions. As we can now construct scattering amplitudes without ever referring to quantum fields and gauge theories, I feel we should change the view on what's fundamental. In particular, when considering that for practical calculations, we fix the gauge anyway, and through field redefinitions we can make the Lagrangian so complicated that the true and fundamental quantum field is unrecognizable, whereas the amplitude is invariant. Yeah, this is very good. This is a more advanced physics question than I usually get, and it's advanced in the particular way that I'm not an expert. So I will give you my opinion, but you shouldn't take my opinion for being very valuable about this. The amplitudes program is an idea that I don't know how far back to trace it. In some sense, it can be traced back to the 60s in the S-matrix program, where people were worried for various reasons about the consistency of quantum field theory. And they said, look, what do you use quantum field theory for? You calculate a scattering amplitude. You just think about, if I have two electrons coming in, what is the probability they scatter off in different directions? And to do that, you sum over all these Feynman diagrams, and they're infinities, and it kind of bugs us. But what we care about at the end of the day, according to this philosophy, is something that is very physical and observable, which is that scattering amplitude. By amplitude, we just mean the thing you square in quantum mechanics to get the probability of this particular result happening. And so people said, well, maybe we don't need all of the talk about quantum field theory. Maybe we should just use very general principles to predict scattering amplitudes all by themselves, rather than getting ourselves tied up in knots with the quantum fields. Now, what happened was that program in the 60s, that program of using general principles to fix all the scattering amplitudes did not work, and quantum field theory was triumphant in various ways, explaining spontaneous symmetry breaking and asymptotic freedom in the strong interactions and things like that, so it kind of went away. More recently, in the good old 21st century, some people doing calculations in supersymmetry, noticed a set of really kind of remarkable things where you would take a scattering calculation in supersymmetric quantum field theories. And the scattering calculation is a sum of Feynman diagrams. There's a lot of Feynman diagrams. You crank through a whole bunch of them. It's a lot of work. You assign your least favorite graduate student who's competent enough to do this task. And then in certain theories, you discover that the answer is a very simple numerical value, right? Pi over 3 or whatever it is. I don't know what the actual number is. It wouldn't be pi over 3. It better be less than 1. Pi over 8. I'm making up the number. Don't believe what the number is. The point is that you've summed up a bunch of terms, each one representing a Feynman diagram. The individual Feynman diagrams give you very awkward, non-analytic numbers, but the sum of them all is a simple number. Again, in these very, very simple cases where you've simplified the quantum field theory problem to something unrealistic, but nevertheless. This is taken as a hint that there is some structure there that is more simple than the Feynman diagrams, more simple than the calculation that you do in ordinary quantum field theory. And so that's not just an aspiration, that is something that seems to be true in these particular cases. So a little mini industry has launched. That's why there's a whole conference, the Amplitudes Conference that Johannes refers to, where people are trying to use, push forward in these ideas. And they've gone way, way beyond what I just described in much more complicated ways that I cannot really tell you about. And it links up with holography in interesting ways and things like that. And this is the origin of when Nima Arkani Hamed says space-time is doomed and things like that. He means all I care about is the asymptotic scattering amplitude, where you start and where you end, not all the stuff in between that is quantum fields moving through space-time. So what do I think about this? I don't know. I mean, on the one hand, the proof of the pudding is in the tasting. If the people who are working on amplitudes are actually able to learn something that we didn't already know about true things about nature, then I'm entirely in favor of both that prospect and the potential actuality of it. I'm not really contributing to it anyway myself, but it seems plausibly promising, if that's not too milquetoasty to say. And so go for it. I hope that I wish them all the best. The obvious worry is that there is more to life than scattering amplitudes, right? But this obvious worry, in other words, sometimes the question you ask in quantum field theory is, I have two widely separated particles. I shoot them toward each other and they scatter off of each other. And that's something that I can calculate. That's most of what you calculate in your first year quantum field theory course. But there's other things you might want to calculate, like the mass of the proton. The mass of the proton is not really a scattering amplitude because the proton is just sitting there and there's things going on inside. But maybe, so the reason why scattering methods are not obviously the right way to go is that I can imagine there are things that I care about other than scattering amplitudes. The reason why that's not necessarily a great reason to be completely skeptical is that holography changes things, right? If you think about the anti-de Sitter conformal field theory correspondence, if you've heard of that, you have a space-time, anti-de Sitter space, and you have a boundary at spatial infinity, which is another kind of quantum field theory, and you can relate what goes on in the bulk to what goes on in the boundary. And so there's this notion that if holography is true, what really matters for what's happening inside is just equivalent to what's happening on the boundary, which is something that is kind of like a scattering amplitude, right? Like it's infinitely far away. You can relate things happening on the boundary to scattering of things that go from the boundary into the bulk and then back to the boundary again. So again, my understanding is very primitive and vague here, but I can imagine that this all is, this sort of marriage of scattering amplitude aspirations plus holography and quantum gravity and things like that will either there's sort of two levels of success. One level of success is this turns out to be a really, really useful tool for doing calculations in what we still think of as quantum field theory. The second level of aspiration is, no, this replaces quantum field theory in some fundamental way. Again, I have no special judgment, no special way of saying whether that's true or false. I think it's very, very interesting and exciting. It's the kind of thing where if you're going to dive in and contribute to it, like there's a lot of very, very smart people who are doing this full time, right? And a whole bunch of them. So if you want to contribute to that particular area, you kind of got to dive in to just keep your head above the water, drop everything else and do that. My level of interest in this area is not so high that I do that. I do have like a tiny little hair of a fraction of an idea that is relevant to scattering amplitudes. And I'm not even going to say what it is because it's too primitive and I need to think about it more. So if 5 years from now I end up writing papers about scattering amplitudes, then, don't think of me as a complete hypocrite, but I'm not diving in both feet first. Let's put it that way. Brandon Lewis says, thinking about the current loss of trust in science has led me to think about expertise in general. How should one decide what subject matter experts deserve our attention when we know very little about a subject? When should we defer to experts and when should we trust our own judgments? Well, I think that I don't have a list or an algorithm or a decision procedure for answering this question. I do admit that it's an important question. We all should be able to do it. But I think that if you're not an expert, and there's not only one person who is an expert, but many, many other people, a vast majority of the experts, and you disagree with them, then you should really, really question your own judgments. Let's put it that way. Like, why in the world, if you are not an expert in something and every expert believes something different, would you not rethink your position? I certainly would. Now, it's much more interesting when there isn't a consensus among the experts, when the experts themselves actually disagree with each other. Then I think that you have a right to sort of listen to their arguments. I think I said this, I said it in another podcast. I've been appearing on a couple of other people's podcasts, Flog the Book and so forth. But when I read a paper and this paper is making outlandish claims, the very first thing I look for is that the authors of the paper recognize that they are making outlandish claims. In other words, they will start the paper by saying, here is why you might very well not believe what we're going to say. Here is why your intuitive reasons are not relevant in this case. In other words, an acknowledgement of why someone should be skeptical. If someone just says, the establishment is out to get me, here's what I think is the truth, then I'm less likely to believe them than if they say, I understand what the establishment is saying, I understand that they have good reasons to do so, here's why I disagree with them anyway. There are various ways to give off an aura of reasonableness, and one way is to admit that you understand and be able to correctly reproduce the arguments for the other side. The other way is, of course, to look at people's track record, right? I mean, are these people just saying that they disagree with the consensus, or have they a track record of disagreeing with this consensus accurately? Have they said many true things in the past? And maybe that's hard to judge, but at some point you need some intermediaries. You need to trust not only the actual subject matter experts, but there needs to be generalists who you trust to tell you who to trust, right? And that trust is never 100%. You should always be willing to change your mind. You should always use your own native skepticism and rationality and so forth. But it's okay to trust some people because we don't live in a world where you can understand everything. There are too many things going on for you to understand everything. Humanity has succeeded in large part because we let other people be experts and trust their judgment. You don't need to know how to build a car to drive the car. Otherwise, you're not going to drive many different kinds of vehicles. Let's put it that way. Ken Wolfe says, listening to the episode with Daron Acemoglu on technology, inequality, and power, it occurs to me that concerns with power and inequality are all about how limited resources are distributed. Stepping back a bit, as technology and AI in particular become more capable, what would ultimately become the final limited resources? If our capabilities to exploit energy and matter continue to build, what is it that power will be used to obtain? Would fame or influence become the new coin? I think that last sentence is a bit of a leap, fame or influence. I can imagine lots of things that one could do with energy or matter, all sorts of calculations, right? I mean, this is clearly something that is going on. We already mentioned cryptocurrencies and AI. Cryptocurrencies and AI are relatively new technologies which share the feature, the sort of large language model kind of AI. They share the feature that they are enormously costly in computational resources. And so enormously costly, right, that they drain a huge amount of power compared to other things going on in the world. It's not hard for me to imagine that trend of inventing new things that I might want to do at the cost of burning a tremendous amount of energy to do them. That could easily continue for quite a while toward the future. But the ultimate resource, to actually answer the question, the ultimate resource is free energy in the physics sense, which means energy that can be put to useful work. Ultimately, that's because we have a certain amount of energy in the universe, and it's in a low entropy form, and we keep increasing the entropy of the universe. It's not a coincidence that these power plants and so forth generate heat as well as waste emissions and things like that. They're increasing the entropy of the universe by quite a bit. What are we going to do with it? I honestly don't know. I mean, I think it's an interesting future question. In some ways, we're still human beings. The sort of 1,000-year time scale is one on which technology will change by a lot. But what makes a human being is not going to change that much. So fame and influence will be important. Power will be important, but also luxury will be important. Entertainment will be important. And also good things like families and vacations and interesting books to read and things like that. They're all going to be important. I don't think any of these things are going to dramatically disappear from the world stage just because we're better at building things that use up energy. Jake Rigby says, you mentioned in your talk with Daron Acemoglu how people compromise themselves for the sake of convenience, e.g. by agreeing to obscure terms to use websites, granting power over their content to the operators. Convenience seems to be at the heart of many of our most self-destructive choices as a species. We take the plane instead of the train. We unsustainably renew our devices for mild improvements in functionality. We accept the conspiracy theory instead of the more subtle explanation, and so on. Unfortunately, these effects are compounding as the convenient choice becomes normalized and then obligatory. Airlines outcompete rail operators on price, forced obsolescence pushes consumers to update, etc. I don't fly, says Jake. I use old tech. I avoid Amazon. I take the time to cleanse my digital footprint, but I am swimming against a tide. Is this spiral inevitable? You don't use very old tech because you left a comment on the Patreon webpage for a podcast. So, when I was born, none of that would be considered old tech, right? It's all relative in some sense. How new or old is the tech that you are using? The spiral is, I wouldn't say inevitable, but pretty darn inevitable. I do think that you're correct. Maybe I'm correct, or maybe Daron is correct. I forget who said it first, but this push for convenience. I also talked about this in my solo episode about the coming phase transition, et cetera. We like convenience. It's very, very hard to get people to intentionally do the less convenient thing for some abstract notion of the good of the planet or something like that. There will always be a plucky minority that take a pleasure in doing that, that want to build their log cabins themselves, but it's always going to be a very tiny, plucky minority. So what is happening is that technology is sort of increasing the efficiency of these trade-offs of convenience versus money. That is to say, the money, the people who run the websites and build the computers and own the factories and run the airlines and the service industries are using technology to figure out how to more efficiently separate human beings from their money by offering them slight more conveniences, not always much more conveniences, right? And that is potentially very dangerous, but it's also enough of a vague worry that it would be hard to know how to, pass a regulation against it or something like that. People have tried. The EU has done better than the United States about, making it easier to reject your cookies or whatever. But we're only going to have more and more complicated technologies that we're dealing with, and the ways in which we turn over our conveniences are only going to be more easier to do that. Not turn over your convenience. It's been a long podcast. Turn over our rights, turn over our data, turn over our privacy in the name of convenience. That's just going to be more and more prevalent. And, I've said this on social media, I guess, but this is at the heart of the realistic version of the AI apocalypse, right? There's a version of the AI apocalypse that says we build an artificial intelligence that is so intelligent that it is more intelligent than us and we can't outthink it. And therefore it will trick us. And therefore, if its values are not aligned with ours, we will be, subjugated or exterminated or whatever. I think that line of argument, which I did not say especially carefully or steelman-y, but it's complete nonsense. It's just a misunderstanding of what intelligence is, what values are, etc. I mean, it has nothing to do with your view on artificial intelligence. It's your views on these ordinary English words that are at risk. But there is an AI apocalypse which just says we're going to use AI and related technologies because they are convenient in ways we don't fully understand. So we will be turning more and more crucial aspects of our lives over to technologies that we can't completely predict or control. Forget about how intelligent they are. What matters is how much we understand them. If we can understand them perfectly and just turn them off, then we're in good shape. But if we can't, then that leads to unanticipated bad consequences. And I think that's a very plausible thing to worry about. I don't think it's going to lead to the extinction of the human race, but very bad things could happen. Let's put it that way. Russell Wolff says, I'm enjoying reading Quanta and Fields. When you talk about the history of the measurement problem, I realized something I'd never thought to ask about. If the Schrödinger equation was developed before the Born rule, how did physicists make sense of it before they had a way of assigning probabilities? Before there was a connection between the wave function and some sort of physical measurement, why would anyone have thought that the equation or even the concept of a wave function was useful or meaningful? Yeah, this is a great question. Like, how in the world do you think that the Schrödinger equation is right if you don't know the Born rule? So the Schrödinger equation came first. So part of the answer is it didn't come that much first, okay? Schrödinger's publication was early 1926, I think, and Born's publication was the middle or late 1926. So it wasn't like they waited 10 years without knowing what to do at a time when there was no email or archive or anything like that. But the other thing is this idea that you measure the wave function and it collapses is very, very relevant to lots of circumstances. But there's some circumstances in which you think that what I care about are the energy levels. I mean, put yourself in the seat of someone who was a mid-1920s physicist. They were thinking about atoms, and they were thinking about electrons in atoms and their energy levels and the radiation that they gave off by hopping between the energy levels. They had the Bohr atom, which was really good for the hydrogen atom, but it wasn't as good for other things. The Schrödinger equation gave you a dynamical equation where you could solve it in various atoms. You could do helium and things like that, and you could get the energy levels. And so then you have to wave your hands and say, okay, somehow the electron hops between the energy levels, and that's the radiation that we see. But they were, in their minds, they were thinking, okay, we'll figure that out later. Schrödinger also had this belief that outside the atom, his equation, not belief, but this aspiration, that his equation would lead to behavior where the wave function actually spontaneously moved towards a more local distribution through space. In other words, if you started with a wave function all spread out, it would become more particle-like over time. So he thought that the wave function was just sort of where the electron was, that, you thought the electron was an individual point, it's really a wave. But the wave is so thin, right? It's so concentrated near one point that it looks like a point to you. That was Schrödinger's hope. Doesn't work at all. In fact, Schrödinger was smart enough to be able to solve the equation, or he should have been, and to show that in free space outside of the influence of an atomic nucleus, wave functions generally spread out more broadly. They do not spontaneously come together. So you needed something like Born's probability interpretation to get the whole picture put together. Leon Enriquez says, I'm pretty sure you've heard of Charles S. Peirce and the New England pragmatists. I wonder if theirs is a theoretical perspective you have explored or are planning to explore. Over the years, I've happily witnessed the expansion of your epistemic perspectives. When I listen to you, I often think Peirce could offer clues to some of the questions you raise, especially with fundamental questions pertaining to idealism, materialism, emergence, mereology, interpretation of theory, etc. Are you planning to delve into Peircean semiotics to relate science and philosophy? Not in any serious way. C.S. Peirce is a very quirky but wonderful figure in the history of philosophy. In fact, he only had one academic position in his life, and it was at Johns Hopkins. And it didn't last because apparently he slept with the wife of one of the administrators or something like that. He got in trouble and he was let go. Apparently he was a bit of a cantankerous personality, as many great thinkers are, but he was wonderfully eclectic, and he knew a lot about lots of things. He knew about math and logic, as well as, pragmatist philosophy. Pragmatism, the cheap straw man version of pragmatism is there's a certain sympathy with the logical positivists, because the pragmatists said, what is the cash value of your idea? You're talking about all this metaphysical nonsense. What does it boil down to? What difference does it make for my life? And they would judge things on that basis. So not only Peirce, but William James, later John Dewey, even Richard Rorty, self-identified as a pragmatist. I'm very sympathetic to pragmatism overall, but I'm not very knowledgeable about all the ins and outs of it. So I'm certainly not going to act like I'm an expert in any of these pragmatist things. If I find some philosophical question that I'm especially interested in, for which these pragmatist perspectives are especially useful, then I will try to educate myself and see what the relationship is. But until that happens, I have other things going on, so I'm not planning a deep dive into Peirce or his friends. Henry Jacobs says, what is the point of hot dogs that are not Chicago style? Oh, now we're getting contentious. Now it's late in the podcast. We can get the real questions getting asked here. For those of you who don't know, there's something called a Chicago-style hot dog, which looks almost unrecognizable to people used to hot dogs from New York or elsewhere in the Northeast. The Chicagoans will take their hot dog and they will pile on, I don't even remember what all the list of ingredients are, but the weirdest thing is like a giant pickle, like a pickle spear. And then, onions and celery salt and little peppers and things like that. There's a lot going on in the Chicago hot dog. The story I was told was that it was a way to get vegetables. It was an excuse to get people to eat vegetables back in the day. I don't know how true that is. But the actual question Henry is asking, what is the point of other kinds of hot dogs? Look, you're not going to be surprised to hear me say that I'm a pluralist about hot dogs, just like many other things. I think that hot dog choice is not determined by the laws of nature. If you like your Chicago hot dogs, then good for you. I would be interested in a scientific study in how much history, one's personal history, affects one's taste later in life. I mean, it's obviously true that you're more comfortable with what you grew up eating, and therefore you might be more influenced by that way. But it's also obviously true that people can discover new things along the way. I wonder what the limits of that discovery process are. Like if you're so locked in to a certain taste profile for something that you literally can't enjoy something that you might have been able to if you had grown up differently. That I don't know. But, there is something that I will defend Chicago hot dogs on, like compared to, let's say, New York, which is that they will most of the time grill their hot dogs over fire or coals or something like that, right? Especially at any good hot dog stand. The quality of the actual hot dog, the actual sausage, forget about what you put on top of it, is generally much higher in Chicago than it is in New York, where they just the street vendors just put their dogs in water and let them sit there. Just terrible. That I will not offer pluralistic apologies for. That's just vile. I will also mention Chicago-style pizza because one of my favorite comics is Tom the Dancing Bug. by Reuben Bowling, which is the pen name for Ken Fisher. I've met Ken. He's a good guy. He mentions Boltzmann brains a lot in the Tom the Dancing Bug comic, which is wonderful. But one of my favorite versions of his comic was from years ago, where he did a, slightly satirical look at Chicago as a city where I lived for 7 years, and I love Chicago very much. And besides hot dogs, of course, there is the pizza controversy. What is the role of Chicago-style pizza in the world of pizza in general? And if you know, Chicago-style deep dish pizza, this is different than pan pizza. Pan pizza, you make the crust in a pan, you put toppings on top. But Chicago-style deep dish pizza, you layer it. So it's almost it's literally like a pie, where there's like a pie crust, and you layer it with sauce and pepperoni and cheese and more sauce and more pepperoni until it's like a thick pie. And the joke in the comic is Chicagoans are proud of having what they think is the best pizza anywhere in the world. And then in small print it says, in fact, it is not pizza at all, but some kind of bread-based lasagna food, which is not wrong, I gotta say, but it's still very, very good. So who cares whether it's pizza or not? That would be my answer to the subtext of the question being asked here. Like what you like. That's what I would say. Cameron Beccario says, shrink machines in TV and movies are fun, but I find them additionally amusing because I assume their characters being shrunk would instantly die due to their biochemical processes no longer being able to work at the new scale. To save them an agonizing death, how might the laws of physics be used or changed to make miniaturization plausible? So as far as I know, there isn't any way to make that happen. In fact, I talk about this in Quanta and Fields because there are the rules of quantum mechanics. There are things called Compton wavelengths. Once you get to be small enough, the wave nature of the particles of which you've made matter. And I think that what Cameron is getting at is something that happens even earlier than that. As you take an atom and shrink it, well, look, what's going to happen if you take a person and shrink them? Either you're reducing the number of atoms while keeping the atoms the same size, or you're keeping the number of atoms the same and shrinking the atoms, or both, of course. Both of those seem very, very dangerous to the human being. If you start removing some large fraction of their atoms, things are not going to work in the same way. You're going to remove some fraction of their DNA, for example? That sounds bad. If you make the atoms smaller, then all of the time scales work differently, right? The rates of chemical reactions are different. The likelihood of chemical reactions are different. So you're not going to get biology to work the same way it does. And this is a classic example. There's much more subtle examples that are also interesting, but a classic example of something that is super easy to imagine, just take a person and shrink them, but actually comes with all sorts of caveats where it wouldn't actually work in the real world. Sorry, Ant-Man. Sorry about that. Connor Kostick says, your conversation with Joel David Hempkins has convinced me to become a pluralist in mathematics. Did he persuade you? So I was already persuaded. I'm already, very much on that side. I'm a pluralist about aesthetics, likewise about mathematics. What else could I be if I'm not a mathematical realist, right? If I think that mathematical systems are things that we construct for purposes in the world. So yes, we can construct different ones. We can have different models to interpret them. I don't believe that there's the one true mathematical system that is the one that it correctly captures reality. AJ says, how well do you think the spherical cow approach to understanding the world is extendable to non-physics fields, both for the hard sciences and other fields like social problems? I think the answer is it depends. I think the answer is, the spherical cow approach of vastly simplifying a hard problem down to its essence, solving that simplified problem exactly, and then adding on all the complications that you neglected to start. You have to figure out whether that works or not. It works for some problems. It doesn't work for others. It works for a lot of problems, a large fraction of the problems in fundamental physics, a much higher fraction than in psychology, for example. But that doesn't mean it can never work in psychology. Maybe there are some examples in psychology where it works perfectly well. I don't know exactly, but I would just caution against deciding ahead of time whether it either does work or doesn't work. Look very carefully to see whether it could possibly work. Brendan Barry asks a priority question. I've become very interested in the ER equals EPR conjecture posited by Lenny Susskind and others, in particular by Juan Maldacena, actually. I understand that the no-signaling theorem is not violated by the measurement of entangled particles. However, some information transfer regarding the measurement's occurrence seems to happen instantly, the spooky action at a distance. In the ER equals EPR conjecture, does the Einstein-Rosen bridge connecting entangled particles effectively localize them, allowing for near instantaneous communication of a measurement, thereby eliminating action at a distance? Is that taking the conjecture too far? I think it's taking the conjecture a little bit too far, but to be honest, I don't think that, well, I know I don't understand the conjecture in that regime. I'm not sure that anyone understands the conjecture in that regime. So the ER equals EPR conjecture is Einstein and Rosen equals Einstein-Podolsky and Rosen, two very different papers that Einstein and Rosen were involved with in the same year, 1935. One, Einstein and Rosen invented what we now call wormholes. The other, Einstein-Podolsky and Rosen, invented what we call spooky action at a distance as a result of entanglement. I think it was Schrödinger who actually used the word entanglement first, but the EPR paper really drove it home. And so ER equals EPR wants to say that there's a way of thinking about entanglement where there's a little tiny wormhole connecting what you think of as entangled particles. Now, that sounds problematic for all sorts of reasons. For one thing, the world is made of fields, not particles, right? For another thing, what does it mean to say a little tiny wormhole? You can't travel through the wormhole. It's not supposed to be a traversable wormhole. So what does it even mean to say that it's there? And a part of the reason why people think it's interesting is because there turns out to be a regime where you can make this kind of conjecture very, very explicit. It's one based on ADS-CFT, where I have two different space-times, okay, two different boundary space-times, so space-times without any gravity in them. So I have two different quantum theories, but then for some reason I glue the space of states together, so I'm allowed to think about joint states of these two spacetimes being entangled with each other. And if I entangle them by a lot, I can imagine that there is an emergent spacetime geometry between them, and that emergent spacetime geometry looks like a wormhole. So when I get maximal entanglement between the infinite number of degrees of freedom in these two spacetimes, it looks like a wormhole. And then the conjecture is that as I go down from an infinite number of degrees of freedom in these two separate spacetimes to just 2 degrees of freedom in the same spacetime, there is still a little bit of a remnant wormhole. I actually don't understand what that means or what it's supposed to mean. Maybe someone else does. I've not dug into it very carefully. So I'm all in favor of thinking about it, but I don't think, I think that it's probably something that is going to be, my prediction would be it's something that's going to be pretty useful and accurate in a certain regime, and we're not yet sure what that regime actually is. Brendan Kay says, one problem with politics is that those who run for national office may win because of their established national fame and or charisma rather than their competency and values. What do you think of a form of sortition where local communities, perhaps at the city or county level, vote to nominate a respected and competent person in their community, perhaps with no election campaign activities or spending allowed, and then one of those people are randomly selected to be president? Maybe that would allow for democracy on a local level, but avoid the national political popularity contest. Maybe it would. I don't think that's a very good system, though, for lots of reasons. For one thing, when you say, perhaps with no election campaign activities or spending allowed, that just seems like a pretty blatant violation of how we think about freedom of speech in this country. Back in the early days of the U.S. Constitution, in the earliest days of democracy here in the U.S., people were still kind of very wary of, they had the monarchy before, right? They were colonies of England, and it took effort to convince people that a democracy would be a better thing, okay? There were some democratic elements to the UK system at the time, but it wasn't full-blown. The king still had a lot of power. And so to convince people that they didn't need a king, they could just do democracy was a big thing. And in the Federalist Papers, one of the things that they had to argue over and over again was that you could have a democracy without people breaking into factions right away. And when they had elections in the early days, as you are reminded if you watched Hamilton, the musical, it was considered somewhat impolite to campaign for an office. You were just supposed to throw your hat in the ring and not be having any political parties or anything like that, and people voted for whoever they thought was best. But that is a very unstable configuration. It doesn't work because guess what? As soon as one person starts campaigning, that person's going to win. So everyone else is going to have to campaign to catch up. And as soon as you have many people campaigning, if they group together to form a political party, they will be stronger and have a more higher likelihood of gaining political power. So any system where you're asking people not to do things in their own best interests is going to be one which I'm skeptical about. The other thing about this kind of sortition idea, get some outstanding members of the community and then pick one randomly, you're going to end up with some people who are really not representative of anything. Maybe, sortition can work. Sortition is the idea that you pick people randomly to be the government of the country. But I think the cases where it empirically works are when you pick like a legislature that way. So you kind of have a large number thing where some weirdos will be balanced out, okay, or will be lost in the larger number of pretty good people. And if you just do this to pick one person to be president, the chances are much higher that that president will be a little goofy one way or another. I'm all in favor of thinking about these different systems, but again, there are always unintended consequences, and so we should try to think of them at the state and local level first before we think of them at the federal level, and we could see what the actual consequences are. Tom James says, in my job as a researcher, I often take digital X-ray images and store them on a computer without looking at them. X-ray images contain quantum noise, variation that results from the exact number and energy of photons that arrive at each detector pixel. Since each pixel in the image would be any integer between 0 and about 66,000, and there are nearly 2 million pixels on the detector, have I just created Schrodinger's hard drive? Does my computer exist in a superposition of 66,000 squared million different states? What will happen if I look at that image? So I think, my knowledge of hard drive technology is not very good, but my strong impression is that file that you're saving is effectively being observed by the environment that it's in. So the whole thing about Schrodinger's cat is that Schrodinger invents a way to put something like a cat in a macroscopic superposition, but the resolution to the puzzle is that decoherence happens very quickly, and that you don't actually have a cat that is in a superposition in the box because the wave function of the universe has branched long before you open the box. And I think the same thing happens if all of those pixels and their measurements are effectively being observed because they move something around on the hard drive where they're being kept, then you're going to have a effectively wave function collapse. Let's put it that way. It doesn't matter that you personally don't observe it. It will be in some particular value, not a superposition of all the possible values. Will says, I've been thinking about poetic naturalism recently, and I'm wondering about when it makes sense to use language like decisions and choices. Clearly, we use this language when talking about what humans do. What about different levels of emergence? Do cells make choices? What about collections of people? Elections come to mind here. For that matter, is it sensible to talk about fluids deciding to flow from high pressure to low pressure regions? So this is a very good question, perfectly good question. I'll say just a couple things. One is that you shouldn't expect a clean and crisp answer to this kind of question. One of the features of emergence is that it typically is an approximation. The boundaries between different parts of the emergent description are generally slightly fuzzy, and the regime in which the emergent description is valid, the boundary of that region is also tends to be slightly fuzzy, okay? So don't ask for perfection here. The question is, to go back to C.S. Peirce, it is a pragmatist question. When does it help you to think in these terms? When does it help you to think about some physical system making choices? If it's a fluid flowing from high pressure to low pressure, do you gain anything by saying, oh yes, the fluid contemplated where to go and then decided to go to lower pressure? I don't think so. I don't think that helps you any at all. There's an equation that directly tells you what's going to happen. That's a much easier way to think about it. For a human being, you give someone a whole bunch of things like, okay, are you going to replace the battery in your electric vehicle? Here are the pros, it'll be more reliable, et cetera. Here are the cons, it costs money. I'm going to let you decide, and then the person thinks about it and decides. I don't have an equation which will tell me in any reliable way what decision that person is going to make. That's a case where thinking of it as something called a decision makes perfect sense. If you have cells or let's say worms or something like that, I don't know. You're going to have to look at it case by case. You're going to have to decide whether or not it's a useful concept to include in your ontology. That's the point. Like, what are the concepts that are really giving you better understandings, better handles over what is going on in the world? If there's a concept that is really, really useful at some level of immersion description, then yeah, treat that as real. Elias Assman says, in quantum fields, you say that quantum gravity, quote, would not be renormalizable. I assume the would refers to if gravity turns out to be described by a quantum field theory. Is it realistic for gravity to be a quantum field theory? And how do we know that it would not be renormalizable? So I'm not exactly sure what I said. I don't have the book right in front of me right here. What is true, what I should have said, is that quantized general relativity is not renormalizable. General relativity is a classical field theory. We have a procedure for taking a classical field theory and quantizing it and asking whether it's renormalizable or not. And the answer is, for general relativity, no, it is not. String theory is renormalizable, and it is a quantum theory of gravity. In fact, it's finite. You don't even have to remove an infinity. You get a finite answer for scattering in string theory. So I personally think that gravity is not going to be a quantum field theory, but we don't know yet for sure. That's something about which we should be a little bit humble. Stevie CPW says, as a basketball fan and intellectual, how do you feel about baseball, a sport that is considered more of a thinking man's game and which currently has division leaders from your own two hometowns of Philadelphia and Baltimore? Look, I'm a pluralist about sports just as much as I am about mathematics and hot dogs. So you're welcome to like baseball if you want to. I grew up as a kid loving baseball, as a Phillies fan. At some point, I don't know, the love that one has for sports isn't supposed to be rationally justifiable, right? It's just something you enjoy. So you don't have to come up with an explanation. Of course, you're tempted to come up with an explanation, but for whatever reason, maybe there's a favorite player that you liked following, or you went to games when you were a kid or whatever. There's all sorts of not completely rational reasons that can go into why you love one sport or another. I fell out of love with baseball. It is fun to go to a baseball game. The fact that it is outside, the fact that it's relatively slow, I forget how many seconds of a baseball game the ball is actually in play, but someone calculated it's a very, very small number of seconds that the ball is actually in play. You can go get the hot dog, come back, put whatever toppings you want on the hot dog, enjoy it in a nice day in the sunshine. That's great. But the game itself is a little tedious for me. Any game where you can play it while 98% of the time you have a beer in your hand isn't the most exciting sport for me. And again, I've said this before about basketball, that there's sort of different modes of reasons why sports can be exciting. Baseball absolutely has super exciting aspects. One of the best aspects of baseball is that very, very let's put it this way. It is much less likely that in a baseball game, the chances that your team, somewhere in the middle of the baseball game, when it's already started and you're near the end of it, the chance that the team that is behind could possibly win is generally much bigger in baseball than it is in hockey, soccer, basketball, football, right? Because there's a clock in those other sports. And if you're down by 20 and there's 5 seconds left in the basketball game, there's no way that you could possibly win, right? That has never, ever happened in the history of basketball. But if you're down by 20 runs in a baseball game and there's 2 outs in the bottom of the ninth, in principle, you could just keep hitting home runs or, base hits and just not get out, and you could win the game. I approve of that aspect of baseball. But my overall, what I care about more, I should put it that way, is the ebb and flow aspect. What I like about basketball is that you score so often, right? And it's not that if you score that often, it is true that every individual basket sort of matters less for the ultimate outcome. But there's absolutely a feeling of, one team is playing better right now. They're scoring more frequently. The other team is playing worse, and that's continuous from moment to moment. It might change from moment to moment, but it's not like a wild, completely unpredictable thing like you could have with a hit in baseball. So I'm glad that there are other sports that other people can like in different ways. I'm also glad that the Phillies and the Orioles are doing well, though the Phillies, I understand, have been stumbling a little bit of late, out of my control. Douglas Stickey says, is it possible to talk about quantum mechanics without using words such as observer, detector apparatus, etc., all of which require the existence of technically advanced humans? Can one talk about quantum mechanics in an imaginary world without sentient beings? Sure, one can. That's what many worlds does. Indeed, that is what almost all of the modern, respectable versions of the foundations of quantum mechanics do in the fundamental formulations of pilot wave theories or spontaneous collapse theories or whatever. There's no fundamental notion of observers or detectors or whatever. However, it is also true that I can say, okay, here's the wave function. It obeys the Schrodinger equation forever. And you're very tempted to respond by saying, no, but that's not what I see. And then I go, now you're interested in you and what you see. So in any of these theories, it is necessary to say how the technical apparatus of the theory, the formalization, maps onto your experience. That was literally Everett's profound idea that you are not a superposition of many different branches. You, at any one time, live in one branch of the wave function. So locating yourself or locating other observers is part of what you would barely call the interpretation of the theory. Jeremy Northrup says, we often make reference to fair coin tosses as a decent enough macroscopic example of the probabilistic behavior of quantum spin measurement outcomes. But what about those fringy non-zero probabilities, at least at the macroscopic level? Even a fair coin toss has at least some teensy non-zero probability of landing directly on its edge and remaining balanced. Certainly the probability would be small, but imagine comparing a dime to a nickel. My question is, are we absolutely sure that the probability of a spin up or spin down measurement is indeed absolutely 1/2 for either outcome always? Or could we imagine some exceptionally weird spin measurement outcome where some near impossible outcome is observed? I mean, taken literally, of course we can imagine that. Maybe someone's elbow bumps into the apparatus, right? I think that literally is a good analogy for the coin landing on its edge. When we talk about a coin flip, that's supposed to be a spherical cow, okay? We're imagining an ideal coin that has zero chance of landing on its edge. Realistic coins deviate from that paradigm and have these other small but possible outcomes. Exactly the same for a Stern-Gerlach experiment with a spin. Of course, it should either go up or down, but maybe someone forgot to turn on the magnetic field and it goes straight. Or maybe it bounces off an atom or something like that and it goes straight for that reason also. So sure, at the literal level, all those possibilities are very, very real. But more importantly, the reason I'm actually answering this question is because we are never absolutely sure that the probability of a spin up or down measurement is indeed 1/2 for either outcome. I realize that it's easy to get that impression because that is very often the example that we use. The correct statement is if you have an electron, or a spin, I should say, whose spin state we know for sure to be in the x direction, or the y direction, either of the directions that is not the z direction, okay? X or y, or any combination of x or y. If you have that kind of spin as your starting point and you put it through the magnetic field, then you get a 1/2 probability of spin up, 1/2 probability of spin down. But it's very easy to make other spin states. You could start with a spin state that was entirely spin up from the start. And then the probability that you get spin up is 1, and the probability you get spin down is 0. So there's nothing special about 1/2, 1/2 when you make these quantum states in the first place, other than it is a useful illustration when we're teaching people quantum mechanics. Okay, very last question for today's AMA. Paulino Sanchez Escribano says, regarding the latest podcast with Daron Acemoglu, and as an economist myself, all the questions about inequality and economic development do seem a bit misguided to me. It is in our nature as human beings to create new things, but also to share with others the fruit of our work. As different studies have shown, a seeming equilibrium tends to develop over time to allow both trends to coexist, even with periods of perceived disequilibrium that lead us to think that one of them is stronger than the other. And the medium that allows this equilibrium to exist is the development of institutions, political, social, economic, spiritual, etc., that tend to be enacted when needed or after a period of serious disruption, like famines, wars, or general turmoil. So here comes the question, do we need new institutions? If so, what new institutions do you consider we humans should be setting up right now to allow this equilibrium to thrive at a time when it seems to be broken? And is it really broken? Yeah, I think that maybe I'm misunderstanding something, but I think that everything you say, Paulino, is exactly what Daron Acemoglu would say. His point is that when you have a major technological innovation causing disruption in the economic system, the first thing that happens is that equilibrium is broken, and generally the breaking happens to the benefit of a small number of elites, rather than to some widespread benefit that goes to all the workers. And then, the workers who are after all, more numerous, will eventually reassert themselves and new institutions will be developed and we will be a little bit more fair. We're still not super duper fair, but at least more fair than we were. And his idea is that by understanding this process, maybe we can shorten the time when the vast majority of workers have to suffer. Right? If we know ahead of time, if we can think about carefully what the bad effects are going to be, then we can ameliorate them. So I think that's completely compatible with what you say. And so you're asking, do we need new institutions and what are the ones we should be setting up? Well, so Daron's answer would be, yes, we need new institutions. I don't know the ones we should be setting up. I think that's a very good question because I don't even know what the technological changes are going to be, really, right? We can sort of dimly perceive that some of them have happened already, but there's plenty more to come. So if he is correct, then there are going to be a bunch of people who take advantage of these new technological innovations in order to sweep up more than their fair share of the wealth, okay? This is not crazy paranoid fantasy talk. This is clearly true. This is clearly what is actually happening. Sam Altman, the CEO of OpenAI, has put forward a plan where the US dollar should be replaced by stock shares in OpenAI, because he thinks there's going to be so much wealth generated by AI that ordinary dollars are going to be pointless and it'd be better to be a share owner in his company. Guess who that would benefit by a lot? So I don't know if it's that we even need new institutions so much as hope that our current institutions are up to the job. I think Daron's point is that they historically, empirically, they probably won't be. But I think at least that being aware of this coming need is a positive thing, right? To understand these kinds of historical things that we've been through before and to see that we're going through it again. And rather than to just let it happen as we've let it happen before, to be a little bit more proactive about it could make things better along the way. That's my very vague, non-professional economist point of view on that. I hate to end on such a vague note, but I hope that we talked a lot about magnetic fields and emergence and things, so I hope that somewhere in this long AMA there is something for everyone. Thanks, as always, for supporting Mindscape. Take care.